All right, people. I believe everybody is doing great, nice, and absolutely fine. So, welcome to Unacademy NEET English. Let me know in the chats if I'm perfectly audible, visible to each and every single student. So, we have the EMI chapter today. We are going to solve every single problem from this particular chapter. And from the scratch, we will be talking about, okay, from the basics. If you haven't studied this EMI chapter before, I'll give you the guarantee before itself that you would be able to solve every problem once we are done with this session, okay? So, tell me guys, and if you have not liked this session, and I would want you guys to smash the like button, okay? Because liking the session is mandatory. Marking the attendance is extremely mandatory, okay? Great. So, we have this electromagnetic induction. Guys, I know EMI is bit related to the magnetism, but I have completed that much of magnetism already when it comes to the last lecture, okay? I know rest of the magnetism is pending, so chill. I'll complete that also either in the recorded format or I'll take that live. So you don't have to worry about anything. So I'll be completing that. That is my job. Okay. So let's finish this electromagnetic induction. Let's finish the electromagnetic induction. When it comes to the electromagnetic induction and AC, we say 2 to 4 questions are asked from these two chapters. Okay. You can see 4 questions. You can say 4 questions because in the recent NEET 4 questions were asked from electromagnetic induction and AC. Okay. And today's session won't be that long because it's a small chapter. We'll be finishing it 5 to 6 hours. So we'll have to finish the chapter in 5 to 6 hours with the maximum number of problems. I have put up almost, I would say, 70, 80 to 100 problems we'll be solving in the today's session. Okay. So I think let's start the session. Everybody has joined. And if you have not liked the session yet, I would want you guys to smash the like button as soon as possible. Smash the like button as soon as possible. Great. Now guys, the first topic that we need to discuss over here, is basically magnetic flux. Guys, see, this is the first topic that we need to understand in this one, that is magnetic flux. Let's suppose I say you have placed a magnet over here. Guys, see, focus now completely over here. Let's suppose you have placed a magnet over here at this particular position. Okay, we know, sir, if you have, let's suppose, placed a magnet over here, we know because of the magnetic field will be there. Yes, sir. Magnet creates the magnetic field. And if I'm saying that this is the magnetic field, because of that magnet. Okay, I'm showing this magnetic field with the help of these lines. So these are basically the magnetic field lines. If somebody asks you, where does these magnetic field lines come from? You simply say, I have placed a magnet over here. Because of that magnet, these are the field lines coming out of the magnet. Okay. Now guys, let's suppose I'll place a surface or a sheet in front of these lines. I'll place a surface over here. Okay. I'm placing a sheet over here in front of these lines. So these are the magnetic field lines coming, and I am placing a sheet over here or a surface area over here. Okay. And let's suppose this surface area is what we call the A. Let's place one more sheet exactly over here. That is this one. That is this sheet. And I call this sheet as B. This is the sheet B. Now, if I say, sir, when it comes to these field lines, they will pass through these two sheets. These will pass through these sheets over here. So something like this. Yes. Now, my question to you guys is, guys, listen to me very carefully. What I'm just saying is that I hope everybody has joined. What I'm saying is that I have placed a magnet over here. Because of the magnet, magnetic field lines will come out. This is the magnetic field lines because of a magnet. And then I place, this is in this region, then I place a sheet in front of these lines. This is the sheet A, small sheet area. Then I place one more sheet over here. We know these field lines will cross. If I ask you, how many number of field lines are crossing through the surface 1, surface A? You'll say 1, 2, 3. So I can say this flux, magnetic flux, that is phi B, will be simply phi B in case of this A. In case of this sheet will be simply 3. And when it comes to how many number of field lines are crossing this surface, and we say 1, 2, 3, 4, 5. So I can say flux through this surface B will be exactly 5. So can I say from now onwards, sir, this magnetic flux is basically how many number of field lines are crossing the surface perpendicularly? Yes. So I can write over here. So magnetic flux is defined as the number of field lines crossing the surface perpendicularly. So whenever from now onwards we say field lines cross any surface, let's suppose there is a field coming over here and it is crossing the board. So we say flux is being created through the board. And more the number of field lines cross through the board, we can say more will be the flux. Less the number of field lines cross through the board, we say less will be the flux. So simply, magnetic flux is how many number of field lines are crossing perpendicularly. Now guys, my simple question to you is, can I say, if I place a bigger magnet over here, from the bigger magnet, we can say large number of field lines will come out. So if more number of field lines are coming out, we say more field lines will cross the surface. So more will be the flux. So I can say this magnetic flux is directly proportional to the magnetic field. More is the magnetic field, more will be the field lines. More are the field lines, more will be the flux. And you can clearly see over here, when it comes to the area of A, area of B, B has got the bigger area. We say through this B, more field lines are crossing. Through this area A, less field lines are crossing. So means flux is also proportional to, we say, sir, area. If area is bigger, if you place a bigger sheet over here, then more field lines will cross through the area. So flux is also proportional to this A. Now guys, can I say combining the two equations, I'll write over here, combining the two equations. So can I say, my dear friends, can I say this flux will be simply, I can write this is B dot, I would say A over here. More is the magnetic field, more will be the flux. More is the area, more will be the flux. And even you can write it something like this also. We can say B dot A is, that is B A cos of theta. So where theta is the, we say angle between, where theta is the angle between magnetic field and area. Where theta is the angle between magnetic field and area. Please tell me in the chats if everything is crystalline clear till over here. I would want you guys to tell me in the chats if everything is crystalline clear. Give me the signal in the chats. Everyone means everyone. Great. Now. If there are students who are having confusion, sir, more is the magnetic field, more will be the flux. We completely agree with you. More is the area, more will be the flux. We completely agree with you. Sir, what is this cos theta? We can't understand this cos theta. See guys. Let's suppose let's suppose I have got a surface over here. I have got a surface over here. I'm placing a sheet. I'm placing a sheet. And in this case, I'm saying magnetic field is something like this. Magnetic field, this is the sheet. This is the sheet. Magnetic field is not crossing perpendicularly, but it is crossing at some angle. It is crossing at some angle. And let's suppose, my dear friends, it is making an angle theta with this, with the horizontal. And guys, see, I would want you to focus over here. If I say, sir, is area a vector quantity or a scalar quantity? We say area is a vector quantity. Like area of this board is a vector quantity. Sir, if it is a vector quantity, what is the direction of the area? We say direction of area is always perpendicular to its surface. So that will be perpendicular to the surface. Okay. So here, if this is the sheet, something like this, so this will be the area in this particular case. Now guys, tell me one thing. We can say B will have two components over here. Sir, first component of B will be, that is B cos of theta, because if the angle is from this side, so from that side we consider cos. And we say this component will be, that is simply B sine of theta. Okay, another component will be B sine of theta. Tell me one thing, guys. Here, which of the two components is crossing the surface? B cos theta or B sine theta? Sir, clearly B cos theta. We say here B cos theta is crossing the surface. And when it comes to the B sine theta, it is just touching the surface. So it will not create flux. That magnetic field only will create flux which crosses the surface. And when it comes to the B sine theta, it is just touching the surface. Now guys, I can say, if somebody asks you what is the flux over here, you say flux in this case will be, sir, magnetic field will be, that is B cos of theta, and area will be simply, that is A. And you can take it over here. Flux in this case will be simply, that is BA cos of theta. So this is the magnetic flux, or you can write B dot A. I hope this is clear. I hope. So basically, we have to take that component of magnetic flux which is crossing the surface. Okay, let me give you one more example. Let's suppose I'll ask you the question over here. Let's suppose I have got a sheet. Over here. This is a plate, or this is a sheet, something like this. I'm placing a plate over here. And in this particular case, I'm saying that there is a magnetic field which is crossing something like this. This is the magnetic field. And this magnetic field is making the angle with the horizontal as theta. And when it comes to the area of this sheet, we say area of the sheet is always perpendicular to the sheet. That is A. Let's suppose I'm taking this A over here. Area of the sheet is A. Okay. Yes. Now guys, if I ask you, find the flux through the surface. Now guys, in this particular case, I would want you guys to focus over here. Sir, this magnetic field will have two components. First one will be this. This will be B cos of theta. Why, sir, cos? Because theta is from this side, so that's why I'm taking this as cos. And another component will be, that is B sine of theta. You tell me one thing over here. Which of the two components are crossing the surface? Is it B cos theta or is it B sine theta? We say here, B sine theta is crossing the surface. And in this case, we say B cos theta is just touching the surface. So we say here, B sine theta is crossing the surface. So if I have to find the magnetic flux over here, that will be simply, that is B sine theta into, we say, sir, area A. So that will come out to be BA sine of theta. So means it is not only cos theta that we are supposed to take. No, we have to take that component which crosses the surface. okay, which crosses the surface. This thing I have told you in case of the electrostatics also. Now guys, if somebody says that, sir, I'll use the general formula. Use the general formula. Use the general formula. What is the general formula? We say, sir, general formula is flux is equal to BA cos of theta. Okay, we'll use this only. Tell me one thing. Sir, this is magnetic field. This is, we say, sir, area. Area is upward. This is magnetic field. And this angle is theta. Total is 90. How much will be this angle? So this will be 90 minus theta. So can I say in this particular case, guys, what is the angle between, we say magnetic field and area, that is 90 minus theta. So I can say this flux will be magnetic field into area, and then I'll write cos of 90 minus theta. Why? Because this theta, we say it is the angle between magnetic field and we say area. Now guys, what is cos of 90 minus theta? We say cos of 90 minus theta is sine theta itself. So I can say flux will come out to be, that is BA, that will be sine of theta. So either if you use this formula or you directly say it something like this, the answer will come out to be the same, that is BA sine theta. Please tell me in the chats if everything is crystalline clear. Everyone. Tell me guys. Okay, great. Now. Let's take a look. Guys, if you have not liked the session, and I would want you guys to hit the like button as soon as possible. Let's take a look at this question over here. Find the flux through the ring. You don't have to find it as of now. Check. I'll write check if the flux through the ring is zero or non-zero As of now, you tell me, is the flux through the ring zero or non-zero? Guys, see, we have got a wire over here. This is an infinitely long wire. Okay, this is an infinitely long wire. And on this infinitely long wire, I'm placing this ring over here. This is the ring. You guys are supposed to tell me, is the flux through the ring zero or non-zero? Guys, see, sir, how flux is created through any surface? Whenever the field lines cross through that surface, we say flux is created. Now, tell me one thing over here. If I am saying that I have got this ring over here, we say current is flowing in the ring. We know this wire, if the current flows through the wire, it creates the magnetic field. So I can say, because of this wire, magnetic field will be created. So place your thumb along the direction of current, curl your fingers. Guys, a current carrying wire produces the magnetic field. You guys know it. If there is a wire, it produces the magnetic field. So because of this wire, we say magnetic field will be produced. How do we find the direction? Place your thumb along the direction of current and curl your fingers. Here, we say direction of magnetic field is inward. So here it is inward from the right side. So this is the magnetic field inward. Now, this magnetic field is crossing the area of the coil, so flux is being produced. Yes. Now guys, I say, what is the flux from the left side of the ring? Place your thumb along the direction of current. Curl your fingers. So it will be outwards. So here, magnetic field will come out to be, it will be outwards. This is B out. Now guys, we say through the ring, the amount of magnetic field which is going in is equal to the amount of magnetic field which is coming out. If this happens, the number of magnetic field lines going in is equal to the number of magnetic field lines coming out. We say in that case, we say net flux is zero. Remember this. Why? Because here flux in is equal to, we say, sir, flux out. Remember this from now onwards. I have told you this in electrostatics also. If the number of field lines going in through any surface is equal to the number of field lines coming out, we say net flux through that surface will be 0. Is this clear? Please give me the signal in the chats. Let's suppose we have this ring over here. This is an infinitely long wire. Now in this particular case, guys, see, we say place your thumb along that. Because of this wire, magnetic field will be created over here. This is the ring. Now, what is the direction of magnetic field? It is completely from the right side of this wire. Place your thumb along the direction of current. Curl your fingers over here. We say if you curl your fingers, it is inwards. So it is inwards. It is inwards. So I can say in this particular case, magnetic flux is not equal to 0. It is non-zero. Why? Because here magnetic field is inwards. So flux will be inwards only. I hope this is clear. Now, let's talk about this. Let's talk about this. Let's talk about this. We have got an infinitely long wire and you have placed a ring around it, something like this. You have placed a ring around it, something like this. Okay. You have placed a ring around it, something like this. See, guys, we say, because of this wire, magnetic field will be created around it. How do we find the direction of magnetic field, guys? It's in 3D. Wire is something like this and ring is placed something like this. So we say, sir, place your thumb along the direction of current, curl your fingers at this point. So curl your fingers at this point. So at this point, magnetic field would be something like this. Similarly, place your thumb along direction of current, curl your fingers at this point. This will be the magnetic field. Here, this will be the magnetic field. Here, this will be the magnetic field. It is like, guys. Place your thumb along the direction of current, curl your fingers. Magnetic field is like this. Here, 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 magnetic field is like this. We say here, magnetic field is forming a circular loop. We say here, magnetic field due to the wire, is forming the circular loop. So if this is forming the circular loop, it is something like this. It is something like this. Guys, don't get confused. We say it is something like this. This is a ring. Okay, and we say here it is forming the loop, something. This is the magnetic field. This is the magnetic field. This is the magnetic field. Now, this magnetic field is not crossing the loop over here. If it is not crossing the loop, we say flux through the loop will be 0, because flux is only created when it passes through the loop. Guys, tell me in the chats if everything is crystalline clear till over here. Everyone means everyone. Tell me, guys. Is it clear? I would want you guys to tell me in the chats if everything is crystalline clear. Why is it not crossing the loop? Because it is, see. This is the wire. See, logically I am saying, at this point, magnetic field would be inwards. If you consider this point only, then magnetic field is inwards. Then there is no problem. You place a ring over here, it will be inwards. But if you check here, it will be something like this. If you check here, it will be something like this, If you join all of these points, so it will form a loop. It will form a loop. Next. We have got a circular ring over here, circular wire over here, in which current is flowing as I. And at the center of this ring, we have placed a square loop. Okay. Find the flux through the square loop placed at the center. This square loop has got the side L. You guys are supposed to tell me what is the flux through this square loop. Guys, tell me one thing. In this particular case, I would want you guys to focus. See, we say whenever you have got a ring and current is flowing in the ring, we say it produces the magnetic field. Because of this ring, magnetic field will be produced at the center. See, guys, how much is the magnetic field because of the ring at the center? We say magnetic field B due to the ring, magnetic field due to the ring at its center, So we say this magnetic field is simply, that is mu naught I divided by, we say 2R. This is mu naught I divided by 2R. This is the magnetic field because of the ring at its center. Now, how do we find the direction? I have told you previously, curl your fingers along the direction of current and thumb is pointing in this direction. So curl your fingers and thumb is pointing outwards. So we say this magnetic field here, it will be outwards. So dot means outwards. So it is and this magnetic field is crossing the square loop. Guys, if this magnetic field is crossing the square loop, don't you think that it will create the flux? Because whenever field crosses the loop, it creates flux. So flux is being created. Now, how do we find that flux? We say that flux will be simply, that is magnetic field into area. Now, what is the magnetic field which is crossing? That is mu naught I by 2R. And what is the area? Area, I am supposed to take area of the loop because it is crossing the area of the loop. And I can say this will be simply, that is mu naught I divided by, we say 2R. Area of the loop will be simply L square. So this flux will be mu naught I into L square divided by, we say 2R. I would want you guys to tell me if this is crystalline clear to each and every single student. Okay. Next. Guys, see. Find the flux through the circular ring. Guys, don't get confused over here. Where does this come from? Because I have told you in the magnetism chapter, because of the ring, magnetic field at the center is mu naught I divided by 2R. This we have already studied in the last lecture. Now guys, let's suppose I'm saying that you have got a square loop over here. And sure, the circular ring is present at the center. What is the flux through the circular loop? See guys, first you guys are supposed to tell me what is the magnetic field because of the square loop. I'll write over here magnetic field due to a square loop. This magnetic field due to a square loop will be simply, that is 2√2 mu naught I divided by, we say pi into L. Because in the last class I told you this is the magnetic field because of a square loop in which the current is flowing. Now guys, see, if the current is flowing through the square loop, we say it is crossing this. How to find the direction, guys? So we say this will be the direction of current, this will be the direction of current. We say, see guys, how we will find the direction. Place your thumb along the direction of current and curl your fingers, it is pointing inwards. Place your thumb along the direction of current, curl your fingers, it is inwards. So this magnetic field will be, sir, inwards. Okay, it is, we say, sir, inwards. If it is inwards, don't you think that it is crossing the loop? And it is crossing the loop. Okay, so if it is crossing the circular loop, so now I can say, sir, flux will be simply, that is magnetic field into area. So I can say flux will be, how much is the magnetic field which is crossing the loop? That will be simply, that is 2√2 mu naught I divided by, we say pi into L. And what is the area of the loop over here? Area of the loop is simply, that is pi r square. And in this particular case, I can say this pi and this pi will get cancelled out. This magnetic flux will come out to be, that is 2√2 mu naught I into r square divided by, we say L. This will be the flux through the circular loop. Please tell me in the chats if everything is crystal and clear. Tell me, guys. So this is the magnetic field because of the square loop. This is the flux through the circular loop at the center. Great, 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 great. Great. Now, guys, we have got an infinite wire over here. Okay. Okay. We have got an infinite wire over here. And at a distance, we have placed this square loop. We are supposed to find what will be the flux through the square loop. You will say, sir, it is very simple. I'll write flux through the square loop will be simply that is magnetic field into area. And here, this magnetic field will be, sir, magnetic field because of the wire. Guys, see. I'm saying that because of this infinitely long wire, magnetic field will be produced at this distance. And how much is the value of that magnetic field? Sir, because of this, it will be B is equal to mu naught I divided by 2 pi R. Now, this magnetic field, find its direction. Place your thumb along direction of current, curl your fingers. This will be inward over here. So the magnetic field created because of this wire is crossing the loop over here. And you are supposed to find the flux. But the question is, this magnetic field is inversely proportional to R. Means as you go away from the wire, we say magnetic field will decrease. So, because of this wire, magnetic field at this R distance will be something. Here it will be, let's suppose this is another R dash. Here it will be different. Here it will be different. So I can say here magnetic field through the loop is different. It is not constant, it is variable. I say if you use this formula, flux is equal to B into A, which value of magnetic field you are going to put over here? Here it is variable. So see, guys. See, I say here magnetic field through the loop. Through the loop is variable. Your magnetic field through the loop is variable. Okay. So you cannot directly use the formula. What you guys are supposed to do is, we say, let's take a small strip of this loop. Let's take a small strip of this loop. Okay. And this strip is, let's suppose at what distance? It is at X distance. And it is very small. So it will be dx width. It will be having the dx width. So I can say, let's take a small strip from the loop. Let's take a small strip from the loop. And I'm saying in this particular case, at this X distance, this strip is present. We say magnetic field at this point will be constant. No doubt if you move away from this, it will be different. Guys, here it is different. At this one point, at single point, it is constant. But if you move from this end to this end, it will be different. But at one point, it is constant. So I can say, and magnetic field at X distance will be, magnetic field at X distance will be. If I ask you, how much is this magnetic field? You say simply, sir, at this X distance, this magnetic field will be B is equal to mu naught I divided by 2 pi X. Because of the magnetic field of, in case of, because of the infinite wire, it is mu naught I by 2 pi R. Cool. Now guys, this magnetic field is crossing the strip. So I can say flux will be created. And it is crossing the strip. So flux is produced. If this field is crossing the strip, so I can say flux is produced. Now guys, if somebody asks you, what is the value of the flux through this? We say if it is a small strip, we say small flux will be produced. So I can say that small flux is what we call d phi. Why? because of the entire wire, entire loop, because through the entire loop, large flux is created. Through the small strip, it is d phi. And it will be simply that is magnetic field into area. Its area is, we say, sir, dA. Okay. And this length over here is L, width is dx. Now, this d phi will come out to be magnetic field at x distance is how much? That is mu naught I divided by, you say, 2 pi x. And what is area over here? Area of this loop, area is L dx, because length into breadth, it's a rectangular strip. Now tell me one thing, guys. To find the total flux, what do? We integrate. I say to find the net flux, we integrate. So I can say that will be integration of d phi is equal integration of, we say, mu naught I divided by 2 pi x L dx. 2 pi x L dx. So what is the integration of d phi, d phi, d phi? This will give us the net flux, and it will be equals to, that is here you can take mu naught I divided by 2 pi L. These you can take out because these are the constants. So mu naught I into L divided by, we say, 2 pi, and here it will be 1 by x and dx, 1 by x dx. Now guys, the question is from where to where you have integrate. And see, you take the first strip at this point, okay, then find the flux through this, that will be d phi. And last strip will be exactly over here, because you are cutting this in infinite number of strips. So last strip will be over here. So you are integrating it from A to A plus L. This distance is A and this is A plus L. So I say this is A to A plus L. So here also I am putting up the limits from A to A plus L. So this flux will come out to be, that is mu naught I into L divided by 2 pi. Mu naught I into L divided by 2 pi, and then we say 1 by, what is the integration of 1 by x? It is ln of x. So I can say this is ln of, then we say x over here. And what is the limits from A to A plus L? And in this case, I can simply say, sir, this flux will come out to be, that is mu naught I into L divided by 2 pi ln of. Now put the upper limit over here, that is A plus L minus A. So then it will become A plus L divided by A. Guys, tell me in the chats if this is crystalline clear. Tell me in the chats if this is crystalline clear. I would want you guys to let me know in the chats if everything is crystalline clear. Okay, tell me guys, is this crystalline clear? Simply, I am saying I took a small strip over here, then I calculated the flux through this strip. Okay. And then, my dear friends, I integrated from this end to this end, and we got the net flux. That's it. Give me the signal in the chats if everything is crystalline clear. Okay. Great. Now guys, see. Let's take a look over here. Now let's discuss the most important law. That is what we call the Lenz law. Let's discuss the most important law, that is Lenz law. And after Lenz law, we'll be talking about the Faraday's law. Okay. Before Faraday's law, I teach that is Lenz law. Let me make you understand this Lenz law. Guys, understand very carefully. Understand very carefully. I would want you guys to focus exactly over here. See. We say, before this, let's suppose I have got, let's do an experiment. Let's perform an experiment. Let's perform an experiment. Let's suppose I have got a wire over here. Let's suppose I have got a wire over here. And this is a circular loop over here. This is a circular loop over here. Circular loop. Or this is a circular wire. Okay? And near to this circular wire, I am placing a magnet. I am placing a magnet. This is a magnet which I am placing near to it. Yes. What I want you guys to do is that, you bring this magnet close to this circular loop. And you bring this magnet, you take this magnet away from the loop, What I'm saying is that, bring this magnet close to the loop and take this magnet away from the loop. Now guys, I say when you take this magnet close to the loop, we say because of the magnetic field lines will come out. Yes, sir. These are the magnetic field lines because of this magnet. Now, when you are taking it close to this wire, close to this loop, don't you think that we say more magnetic field lines will cross the loop? Yes. When you take it away from the loop, we say less number of, because some will go from like this, some will go something like this. So we say then less number of magnetic field lines will cross the loop. So we say, I'll write the same statement on bringing magnet close to the loop, On bringing magnet close to the loop, we say magnetic field lines through the loop will increase. Okay, so more number of magnetic field lines will cross the loop. And if we take the magnet away from the loop, we say less number of field lines will cross the loop, So basically, if you take the magnet away from the loop, we say number of field lines through the loop will decrease. I'll use that statement. Number of field lines through the loop will decrease. Okay. And guys, experimentally we saw that whenever the number of field lines through the loop increase or decrease, we say, sir, flux will increase or flux will decrease. So we saw that, and we observed current is induced in the loop. Guys, this is the experiment we are performing. When we take this magnet close to the loop, we say more number of field lines will cross the loop. So we say flux through the loop will change. So we saw that current in the loop is being created. Let's suppose this is the current which is being produced. And when you take this magnet away from the loop, in that case also current is being created. So means whenever the flux through the loop changes, we say current is being induced. So whenever current through the loop, whenever magnetic field, field through the loop changes, current is induced. Okay, this itself is called the Faraday's law. So we say current is induced. Now the question is, okay, sir, we got it. what is the direction of the current? Now, we say direction of that current. Direction of that current is given by, we say, Lenz law. Direction of that current is given by Lenz law. So we say simply, direction of that current is given by Lenz law. So if you place the magnet at one particular position only, we say, sir, in that case, number of field lines through the coil will not change. It will remain constant. We say no current is induced. So current is induced only when you take magnet close to the loop, when you take magnet away from the loop. So we say current is induced in the loop. Okay. Now guys, how to find the direction of current? That is because of the Lenz law. Okay. How to find the direction of the current? That is because of the Lenz law. Now guys, I would want you guys to understand one thing over here. See. In this particular case, what does the Lenz law says? Lenz law says that direction of induced current will be in such a way, that it opposes the cause due to which it is induced. Now see, I'll tell you the direction of current. Now guys, see. I'll tell you the direction of the current. We say, if the primary magnetic field, is increasing, the current in the coil will try to decrease it. Guys, I'll make you understand this. And if the primary magnetic field means the magnetic field because of this. So this is what we call the B primary. If this B primary is increasing, how it is increasing? When you take it close to the wire, when you take it close to the loop. So we say, if the primary magnetic field is decreasing, we say the current in the coil will try to support it. I'll make you understand. Now guys, tell me one thing. In this particular case, guys, see. We say, because of this, if you are bringing it close to this wire, okay. And my dear friends, we say this primary magnetic field through this coil, this is the primary magnetic field which is crossing. This primary magnetic field is increasing because you are taking the magnet. Now, this current will be in such a way so that it will try to decrease the primary magnetic field. Why? Because it is increasing. So how am I supposed to make the direction of the current? We know current will flow because the magnetic field is changing, current will flow. The direction of the current, guys, if I make it something like this, see, if I make it something like this, what is this in this particular case? So I am saying, if I am making the direction of the current something like this over here, guys, something like this. And what is this? Anti-clockwise. So if I make the direction of the current in anti-clockwise direction, we say, now this current will produce one more magnetic field. Why, sir? Because whenever the current flows through the coil, it produces the magnetic field. So because of this current, another magnetic field is being induced. That is what we call the secondary magnetic field, and that will oppose this. That will be in this direction. This is B secondary. Now see, this secondary magnetic field is opposing the primary magnetic field. Guys, see, if this is a coil, through the coil, the magnet is coming close. So field lines through the coil will increase. So primary magnetic field is increasing. Because of this changing magnetic field, current in the coil will start flowing. Now, How to make the direction of current? If primary magnetic field is increasing, you have to make the direction of current in such a way so that it will oppose this primary magnetic field. Make it in anti-clockwise direction. If you make it in anti-clockwise direction, it will create one more magnetic field, because we know whenever the current flows in a magnetic field, it creates whenever the current flows in a coil, it creates magnetic field. How to find the direction? Curl your fingers along the direction of current. Thumb will be pointing in this direction, so thumb is opposite to this, so secondary is opposing the primary magnetic field. So I can say in this particular case, direction of current is, we say anti-clockwise. Now guys, see. I'll solve more than 25 questions on this law, so you don't have to worry about it. As of now, you just remember the statement. If the primary magnetic field is increasing, the current in the coil will try to decrease it. If primary magnetic field through the coil is increasing, so current will be in such a way so that it will oppose it, it will decrease it. If the primary magnetic field is decreasing, the current in the coil will try to support it. Now, let's move on to the question. Wait. Guys, see, we have got, this is a coil over here, square loop over here. Primary magnetic field is outward. And it is given as primary magnetic field, B primary, it's increasing. And it is outward. Now, guys, tell me one thing. If you place the coil in the external magnetic field, which is increasing, we know that, sir, this coil will oppose the increasing magnetic field, and it supports the decreasing magnetic field. Now tell me, if primary is increasing and is outward, now guys, if you want to oppose the outward magnetic field, how will you oppose it? Sir, you have to create the secondary magnetic field in the inward direction. This is B secondary and this is B primary is outwards. Okay, so if you guys, if I say magnetic field is in this direction, primary, you have to oppose it. You will apply the magnetic field in opposite direction. If you want to support it, you will apply the magnetic field in same direction. Here, primary magnetic field is increasing and it is outwards. Dot means outward. If you want to oppose it, you have to apply the secondary magnetic field in the inward direction. We say B secondary should be inwards. And how this secondary magnetic field is being produced, we know. Whenever you place a coil in the changing magnetic field, current is being induced. So current is being induced. Because of this current, secondary magnetic field is produced. Now, tell me, if B secondary is inwards, how should be the direction of the current in the coil? I think if you place the current in this direction, sir, clockwise. So now curl your fingers along direction of current, thumb is pointing inwards. So then only it can create the magnetic field which is inwards. So I can say in this particular case, we say current is clockwise. Okay, so if current is clockwise, then only secondary magnetic field will be inwards. Then only that will oppose the primary magnetic field. Otherwise, that is not possible. Please tell me in the chats this is clear. Guys, let me know in the chats if it is crystalline clear. And smash the like button if you have not liked the session yet. Give me, I'll solve more questions, so chill. Tell me, is it clear till over here? So what does Lenz law say? Lenz law says that if primary magnetic field through the coil is increasing, you oppose that primary magnetic field. If primary magnetic field through the coil is decreasing, you support that primary magnetic field. Okay? Now, guys, Now see, find the direction of the current, induced current. Guys, in this particular case, we say B primary, we say is decreasing. And it is outwards. Now, when it comes to the decreasing magnetic field, we support it. So I can say in this case, B secondary has to be inwards. Okay, sorry, outwards. B secondary has to be outwards. Why? Because here, primary magnetic field is increasing. Is it increasing? Okay, sorry. And in the previous case, it was what? It is the same question. Okay, let's make the primary magnetic field decreasing over here. Okay, so B secondary has to be outwards. Why? Because we support the decreasing magnetic field. So how will you support? If you apply the secondary magnetic field in the same direction? So we say in this case, B secondary has to be outward also. And how can you create the secondary magnetic field in the outward direction? If the direction of current in this case is anti-clockwise. If the current flows in the anti-clockwise direction, then only the secondary magnetic field will be outwards. How? Curl your fingers along direction of current, thumb is pointing outwards. So I can say I will be anti-clockwise. Next, let's talk about this one. Find the direction of the induced current. Okay, guys, tell me one thing. You have got a wire over here. In this wire, current is flowing in the upward direction. And there is a loop over here. And this current is increasing. Because of this current, magnetic field will be produced over here. Place your thumb along direction of current. Curl your fingers at this point. So it will be outwards. So because of this current, magnetic field here, it will be outwards. Magnetic field will be outwards. So this will be primary. And if the current is increasing, because of this current, increasing current, primary magnetic field will be increasing. So we say here B primary is increasing and it is outwards. And if you are placing a coil in the outward magnetic field which is increasing, we say, sir, we oppose the primary magnetic field. We oppose the increasing magnetic field. B secondary should be inwards. So how you are supposed to do that? Sir, if B secondary is inwards, that is only possible if the direction of the current is clockwise. So I is clockwise over here. Because when the current flows clockwise, then only secondary magnetic field will be inwards. Let's talk about this one. Find the direction of the current. Guys, see, in this case, this current in this wire, this is an infinitely long wire. Because of this current, we say this current is decreasing. Now, tell me one thing. Because of this, magnetic field in here will be in which direction? Place your thumb along the direction of current. Curl your fingers at this point, it is inwards. So because of this, magnetic field here is inwards. So B primary in this case is inwards. And if the current is decreasing, because of the decreasing current, we say this magnetic field will be decreasing. If primary magnetic field is decreasing, what you guys are supposed to do? Are you supposed to support the decreasing magnetic field or oppose? We support. So I can say here B secondary should be inwards. Okay. And if B secondary is inwards, how is that possible? If the current in this is, we say clockwise, because in case of the clockwise current, curl your fingers along direction of current, thumb is pointing inwards because of this. So I can say current has to be clockwise. Guys, give me the signal in the chats. I hope now it is crystal and clear. I hope now it is crystal and clear. Let's talk about this one. Let's talk about this one. Let's talk about this one. Great. Now, guys, here in this particular case, you have got a wire in which current is flowing, and this is a constant current. Current is not changing over here. This is a constant current. And this square loop is going away from the wire. This square loop is going away from the wire. It is moving with a velocity v. As the loop is going away from the wire, we say magnetic field will decrease, because as you move away from the wire, magnetic field will decrease. So we say here magnetic field through the loop will decrease. Why? Because it is moving away from the wire. And what will be the direction of magnetic field? Place your thumb along direction of current, curl your fingers. So here magnetic field is inwards. This is the primary magnetic field. Okay. And when it comes to this primary magnetic field, I can say this primary magnetic field is decreasing and it is inwards. And when it comes to the decreasing magnetic field, we support the decreasing magnetic field. So in this case, can I say, sir, B secondary should be also inwards? Because if primary magnetic field is inwards and is decreasing, we have to support it. How will we support? By applying the magnetic field in the same direction. We say B secondary should be also inwards. B secondary should be inwards. B secondary should be inwards. So that is only possible if the direction of the current, is what? Clockwise. So I say I is clockwise. Okay. Next, let's talk about this question. I'll take the ray optics once we get done with these chapters. Okay, after these we'll be taking that. Is it clear? Give me the signal in the chats. If everything is crystalline clear, tell me, guys. Great. Now, guys, see. Okay, take a look over here. Find the induced current in the loop ABC. Guys, see. This loop is moving away from the wire, constant. It is the question exactly similar to this one. Loop is moving away from the wire. So magnetic field through the loop will decrease. So secondary magnetic field should be also inwards. Current is clockwise. Same question. Here current is clockwise. This is the direction of the current. This is moving towards the wire. This is the loop C. So I can say, guys, we say, place your thumb along direction of current, curl your fingers. In this case, this is the direction of the primary magnetic field. This is B primary. Can I say in loop C? We say in loop C, I can say this B primary is increasing. Why? Because if the loop is moving towards the wire, we say magnetic field will increase and it is inwards. Now tell me one thing. Do we support the increasing magnetic field or oppose? We oppose it. So in this case, we say B secondary should be outwards. Okay, outwards. Because then only we can oppose it. So how is that possible? If the direction of the current is anti-clockwise. So if current flows in the anti-clockwise direction, we say then only it creates the magnetic field in the outward direction. Okay, and here I can say current in this case will be 0. Why? Because it is moving some parallel to the wire. No magnetic field line through the loop will change. Why? Because here, the number of magnetic field lines crossing here will be same here, because it is moving parallel to the wire. So current in the first loop is 0. Now let's suppose if we have a question something like this. Find the direction of the induced current in the loops. See guys, you have got a wire over here. The direction of the current is this downward, and it is increasing. Because of this increasing current, tell me, what is the direction of the magnetic field in loop A? Place your thumb along direction of current, curl your fingers. So here, this B primary is increasing. This B primary is inwards. Okay. So I can say in loop 1, in loop A, can I say this primary magnetic field, it is increasing? Primary magnetic field is increasing and it is inwards. Now, we say here in this case, current will be induced and that current will oppose the primary magnetic field. So in this case, I can say secondary magnetic field should be outwards. Why? Because primary is inwards and it is increasing. So how is that possible? If the direction of the current, is anti-clockwise, okay? If anti-clockwise current flows over here, because of that, secondary magnetic field will be, we say, sir, outwards. I hope this is clear. Now tell me in this loop, guys, see. When it comes to this loop, this is the current. Okay, this is the current flowing something like this. Place your thumb along direction of current. Curl your fingers. So we say here, primary magnetic field is outwards. Because of this wire, primary magnetic field is outwards. So I can write over here, in loop B. In loop B. I can write over here in loop B. We say in loop B, I can say this primary magnetic field is increasing. Why? Because current is increasing, magnetic field will be increasing. So we say this is increasing. Primary magnetic field is increasing and it is outwards. Okay. Now I can say clearly in this particular case, secondary magnetic field should be inwards. Because then only it will oppose the primary magnetic field. And that is only possible if the direction of the current is clockwise. So we say here, B secondary should be inwards. That is only possible if the direction of the current is, we say, sir, clockwise. Okay. So I can say current in this particular case is clockwise. I hope this is clear. Next, let's take a look over here. Guys, this is a region of constant magnetic field. A region of uniform magnetic field. This is the region of uniform magnetic field. We have got a loop over here. So this loop is moving inside and the circular loop is moving inside the constant magnetic field. This circular loop is moving inside the constant magnetic field. You guys are supposed to tell me what will be the direction of current at point A. What will be the direction of the current when it is just entering the loop at B, at C when it is inside, at D when it is coming out? Guys, tell me one thing. We say at A, the loop is completely outside the magnetic field. No field line is crossing the loop. No magnetic field is changing. So I can say in this case, current will be 0. Current is only produced when the magnetic field lines through the loop will change. Here it is not changing, here it is 0. Now, when it is going inside, I can write over here at B. When the loop is going inside, don't you think that more number of field lines will cross through the loop? Yes. So we can say field through the loop is increasing. We can say, sir, magnetic field is increasing. And it is inwards because the direction is given over here. It is cross means inwards. Now guys, if it is increasing and inwards, we oppose the primary increasing magnetic field. So primary is increasing. We say B secondary should be. We say should be. In which direction? In which direction? We say, sir, outward. Okay. And I can say here, this B secondary has to be outward. That is only possible if the direction of current is anti-clockwise. Here, this is the direction of the current. So I can say current is ACW, anti-clockwise. Now guys, when it comes to the point C, at point C, number of field lines crossing this will be constant because it is completely inside. It is not changing. From here to here, number of field lines is constant, same. So in this case, current will be 0. Because whenever the magnetic field through the loop is constant, we say current will be 0. Current is only induced when the field lines change, increase or decrease. We can say then at D, I'll write over here, at point D. Tell me one thing at point D. Can I say the loop is coming out? So field lines through the loop will decrease. I can say magnetic field primary will decrease. Magnetic field primary will decrease. If primary magnetic field through the loop decreases, so we say and primary magnetic field will decrease. So in this particular case, I'll just write over here decreasing and it is inwards. So we say secondary magnetic field will be also inwards. Why? Because we support the decreasing magnetic field. So I can say B secondary is inwards. B secondary is inwards. Okay. So secondary magnetic field is also inwards. If secondary magnetic field is inwards, that is only possible if the direction of the current is clockwise. So here, B secondary is also inwards. So direction of the current has to be clockwise. Give me the signal in the chats if this is crystalline clear, this question. Tell me guys if this is crystalline clear. Tell me. Now guys, in this particular case, I would want you guys to focus over here. Find the direction of the current with respect to the observer. With respect to the observer. Sir, what kind of question is this? Yes, it is a very logical question. It is a very logical question. See, let's suppose I say I have got a coil over here. This is a coil. And in this coil, current is flowing something like this. In this coil, current is flowing something like this. Guys, with respect to me, it is clockwise. If it is flowing something like this. Now focus. I'll go from onto this side. Now it was flowing in this direction. Now with respect to me right now, it is flowing in anti-clockwise direction. So if you change the position, we said direction of the current changes. So here, this is the coil, current is flowing in this direction. So it is clockwise, tuk, clockwise. Now if you move on to this side, same direction becomes anti-clockwise for me. So that's why we say observer is mandatory in this particular case. Find the direction of the current with respect to the observer. Here we remember a trick in this particular case. And I would want you guys to remember the same trick in this particular case, because then only you would be able to solve every single problem from this particular chapter. then only you would be able to solve every single problem from this particular chapter. Okay. Now guys, focus completely over here. Okay. Now see. This magnet is moving away from the coil. This is the coil. The magnet is moving away from the coil. Tell me one thing. If the magnet moves away from the coil, we say magnetic field through the coil decreases. Magnetic field through the coil decreases. What does the Lenz law say? Lenz law says that we support the decreasing magnetic field because we don't want the magnetic field through the coil should decrease. So this coil never wants that magnetic field through it should decrease or increase. So we say the coil never wants the magnetic field through it should increase or decrease. The coil never wants that the magnetic field through it should either increase or decrease. Yes. Now guys, if the magnet is moving away from the coil, we say the coil will support that magnetic field because it is decreasing. If it is moving towards the coil, it will oppose that. Now guys, see. Please focus over here. So here we say this coil will kind of create the imaginary bar magnet. This coil will kind of create the imaginary bar magnet. This coil will kind of create the imaginary bar magnet. And north pole will be from this side, south pole will be from this side. Why? Because south pole of this bar magnet is here, north pole of the bar magnet is over here. See guys, this north pole will attract the south pole. So means that the coil does not want the magnet should go away from it. It should not decrease. So that's why it created the north pole over here, and because it can attract, unlike poles attract, it will attract, it does not want the magnetic field should decrease. If it was something like this, guys, if it was, this is the coil, and I am saying this is over here, north pole, this is south pole, and it is going towards the coil. Now, when this magnet goes towards the coil, magnetic field will increase. This coil opposes the increasing magnetic field. So it will create the imaginary bar magnet over here so that north pole will be from this side, south pole from this side. Why? Because north repels north. Coil will never want that magnetic field through it should increase. It should go close to the coil, so it will oppose that. And even if let's suppose I'm saying this is a magnet, this is south pole, this is north pole, in that case it will create south pole from this side so that it will repel it. So I hope this is clear. In this case, this is moving away from here. This is the imaginary bar magnet. Okay, it is created by the coil. Now guys, tell me in this case, see, you have to remember one thing. What is that? We say, now this observer is able to see which pole, north or south pole in the coil. We say, sir, it is directly able to see north pole. So I can say, if the observer sees north pole in the coil, then current is anti-clockwise. Okay, and I'll write over here, if the observer sees south pole in the coil, then the current is clockwise. Now tell me, in this case, observer is able to see north pole. So here, So here I can say I is anti-clockwise. This is the simple trick that you guys are supposed to use. In this case, we say current will be anti-clockwise. Let me give you one more question. Guys, see. You have got coil A, you have got coil B. You have to find the direction of current. The magnet is moving towards coil B. It is moving away from the coil A. We say here imaginary bar magnet will be created and north pole of the bar magnet will be over here south. Why? Because north attracts south. The coil does not want this magnetic field through the coil should decrease, or this magnet should go away from the coil. Also, this coil does not want this magnet should come close to it. So it will create the imaginary bar magnet. This will be north pole, this is south, because north will repel north. Now tell me, this observer is seeing which pole of this magnet? Sir, observer sees south pole over here. So I can say current in this case is clockwise. Current in the coil A. This observer is able to see which pole in the coil B? North pole. Because another side is, we say, south pole. Another side is, we say, south pole. So I can say in this particular case, current in the coil B is, that is simply anti-clockwise. It is anti-clockwise. Okay. Please tell me in the chats if this is crystalline clear. Guys, tell me. Guys, tell me if this is crystalline clear. I would want you guys to give me the signal in the chats with the fire emojis if this is crystalline clear. If the observer is able to see the south pole, because observer is directly facing the south pole, so means it is seeing the south pole. Okay. Observer is facing the north pole because it is seeing the north pole. So here it will be this. Okay. Why is there repulsion in one coil and attraction in another coil? Because I have already explained this in the Lenz law. Lenz law says that whenever the magnetic field through the coil changes, it will oppose the cause which is producing it. If it is increasing, it will oppose it. If it is decreasing, it is supported. That's why oppose means it is the primary magnetic field is increasing. That's why it is repelling. And through coil A, it is decreasing. That's why it is attracting. Great. Now guys, let's take a look over here. We have got two coils. This coil, in this coil, we say current is decreasing. What will be the direction of the current in the inner coil? Find the direction of the current in the inner coil. Guys, tell me one thing. Because of this current, magnetic field will be produced over here. Let's find the direction. Curl your fingers along the direction of current. Thumb is pointing inwards. Because of this current, magnetic field here will be inwards. Okay? Okay? Yes. Now, through the second coil, we say through the inner coil. Inner coil. Guys, we say primary magnetic field, this, which is created because of this coil. So it will be decreasing. Why? Because primary current is decreasing. Okay? Okay? And in this case, it is inwards. It is inwards. It is inwards. Now tell me one thing. Tell me one thing. If primary current is decreasing and is inwards, tell me one thing, my dear friends. I would want you guys. See, we say through this coil, magnetic field is decreasing. So we have to support the decreasing magnetic field. We say secondary should be also inwards. Okay. So we say B secondary. This is primary. So B secondary should be also inwards. That is only possible if the direction of the current is in the clockwise. So I in this case is clockwise. I in this case is clockwise. Yes, great, great. I in this case is clockwise. Next, let's talk about this one. Let's talk about the wire changes to a circular shape. We have to find the direction of the induced current. Okay. Guys, see. Here, this magnetic field is constant. And you have placed a loop over here. And it is changing its shape to circular, means here. I can say here, area of the loop is increasing. Okay. In this case, no doubt magnetic field is constant, but area of the loop is increasing. Now tell me one thing. We can say flux is equal to magnetic field into area. We say if flux through the loop increases, or when magnetic field increases means flux increases. So this flux depends upon magnetic field, this flux depends upon area. Or simply you say, forget about the flux over here. If we say area of the loop is increasing, we say more field lines will cross. So more field lines will cross the loop. If more field lines will cross the loop, so means through the loop magnetic field is increasing. So I can say through the loop magnetic field. So I can say B primary is equal to increasing through the loop. Okay. And it is inward and it is inwards. Now you tell me one thing. Do we support the increasing magnetic field or we oppose the increasing magnetic field? I can clearly say in this particular case, we oppose the increasing magnetic field. So I can say B secondary has to be outwards. Okay. And that is only possible if the direction of the current in this particular case is what? We say anti-clockwise. Because then only the secondary magnetic field will be outwards. Curl your fingers along the direction of current, thumb is pointing outwards. So I can say current in this particular case will be ACW, that is anti-clockwise. Okay. We say in this particular case, this is a square loop. And there is a positive charge, which is basically here, the positive charge is moving towards the loop, and then goes. So here initially it is moving towards the loop and then goes away from the loop. So initially it is moving towards the loop, then it is moving far from the loop. Tell me one thing. Guys. If charge is moving, we say current is being produced. So I can say in this particular case, this will be the current. Direction of positive charge is the direction of current. So now tell me, guys, you can consider this as a wire over here. When it is away, we say, and it is moving towards the loop. Guys, this charge is moving towards the loop means wire is coming close to the loop. So I can say magnetic field through the loop is increasing. I can say when charge moves towards the loop, when charge moves towards the loop, then magnetic field will increase. Then what is the direction of magnetic field? Place your thumb along direction of current. Curl your fingers. So it is outwards. So B primary. So I can say B primary in this case is outwards. So I say B primary is outwards, and it is increasing. And if it is increasing, my dear friends, you tell me one thing. You tell me one thing. What will be the direction of the current? Sir, we have to oppose the increasing magnetic field. So B secondary, I can say B secondary in this case should be inwards. So I can say B secondary is inwards. B secondary is inwards. Okay. So I can say B secondary is inwards. And that is only possible if the direction of the current in this case is, so I can say current has to be, we say clockwise. So we say current has to be clockwise. We say current has to be clockwise. Okay. Now guys, the second case is when charge moves away from the loop, when charge moves away from the loop, in that case we say magnetic field will decrease, then B primary will decrease. Okay, then B primary will decrease. And if B primary decreases and direction of the primary magnetic field will remain outward only, because here also it is outward and it is outwards. Okay, so we support the decreasing magnetic field. In that case we say B secondary should be also outwards, because magnetic field is decreasing, so we support the decreasing magnetic field. That is only possible if the direction of the current is anti-clockwise. So I say current in this case will be anti-clockwise. Is this clear? Is this clear? Is this clear? Is this clear, guys? Is this clear? Give me the signal in the chats. Give me the signal in the chats. I would want you guys to tell me. Great. Plot the graph between acceleration versus time. If a magnet is falling and you have got a coil over here. This is a coil. Guys, see. In this case, I am saying that you have got a magnet. You have got a coil. This is a circular coil over here and you have a magnet. If you're releasing this magnet, we say it will fall and it will cross this magnet. It will cross this coil over here. You have to plot the acceleration time graph. Guys, very important question. And if you have not liked this session yet, hit the like button as soon as possible. See guys. In this case, I'll write over here case 1. Case 1. What is case 1? See. We say when magnet is very far, means the coil is over here, you have placed the magnet at very far distance. So we say there is no connection between coil and the magnet. It will not oppose, neither it will oppose nor it will support. Because it will oppose and support only if the magnetic field through the coil changes. When it is very far, in that case, we say acceleration will be simply G. Acceleration will be G. Okay. Yes. And then, my dear friends, when case 2, when I say this magnet is coming close, when the magnet, so I'll make it something like this. Okay, case 2. My dear friends, this is the coil over here and this is the magnet over here. Okay, and it is moving something like this. We say this is south pole and this is north pole. And when it is moving towards the magnet, do you think that, sir, magnetic field through the coil will increase? Why? Because the magnet is coming close to the coil. And we know that the coil will never want the magnetic field through the coil should increase. So it will oppose, this will be the secondary, this will be the imaginary bar magnet. So here it is north pole, here it is south pole. So it will oppose. And if it is falling with the acceleration A is equal to G over here. So here acceleration is acceleration due to gravity, means if you release this object, it falls with the acceleration due to gravity. So here in this particular case, we say acceleration will be less than acceleration due to gravity. Why? Because now the coil is opposing it. Now the coil is opposing it. So the acceleration will decrease. Okay. And my dear friends, in this particular case, when it is case 3, we say, sir, 3 over here, case 3. So when I say it crosses the coil, when it crosses the coil means when it is exactly over here. So this is the magnet, this is the south pole and this is the north pole. Do you think that this coil will want the magnetic field should decrease through it? This magnet should go away from it? We say, sir, no. So it will create the imaginary bar magnet over here, and north pole will be from this side, south pole will be from this side. So again, it will attract. Okay, we say here a repulsion. Here it will be repulsion. And in this case, we say there will be attraction. There will be attraction. So if it is going away, so there will be attraction. Again, here acceleration will be less than G. Acceleration will be less than G. Okay. Again, acceleration will be. Is this point clear till over here? Guys, tell me in the chats. Is this point clear till over here? Tell me. So when the coil is very far from the magnet, in that particular case, we say, there is no repulsion, there is no attraction. When it is close to the coil, there will be repulsion. Okay? At the time of entering the coil, at the time of leaving the coil, there will be attraction. Okay? And then when it goes far, okay? So again, there will be this. And one more thing, when it is exactly at the middle of the coil, there will be no attraction. There will be no attraction, no repulsion. Guys, 3 cases I discussed over here. 3 cases. When it is coming close, acceleration will be less. When it is leaving, okay, when it is leaving, acceleration will be less. Okay. When it is exactly at the center, let me show you over here. Guys, this is the coil. And in this particular case, here we say this is south north. This is south and this is north. We say it will create over here north and this is south. So here it will be repulsion and acceleration is less than G. And then let's suppose when the magnet exactly reaches over here, okay, in the middle. So we say here acceleration will be equal to G. There is no repulsion, no attraction. And then we say, if this magnet is leaving, this is south, this is north. We say it will create the bar magnet. This will be north, this will be south, there will be attraction. And here acceleration is less than G. Now, if we plot the graph, guys, see, if we plot the graph, acceleration versus time. Guys, initially it is falling with acceleration due to gravity, then it decreases, and here it is acceleration which is less than G. Acceleration is less than G. And at the time of entering, exactly at the center, what is the acceleration? Acceleration is equal to G. So again it will increase. Here acceleration is equal to G. And then my dear friends, at the time of leaving, again acceleration will decrease. So if again acceleration decreases, so it would be something like this. So when it goes far, when it reaches over here, it will keep on falling with the acceleration due to gravity. So I can say again the acceleration will increase and then it remains constant. Okay, A is equal to G. I hope this is clear. Guys, when it is about to enter, it will face repulsion, so acceleration will decrease. So this is at the center. We say at the center of the coil. At the center of the coil. Guys, give me the signal in the chats. Is this graph clear? Is this graph clear? Please tell me in the chats. Everyone, tell me. Is this graph clear? Let me give you one more example over here. Let me give you one more example over here. Where is that? Where is that? See. Here solenoid is. Solenoid I didn't teach you in the magnetism. Just remember it directly. In this particular, solenoid is basically the coil of many turns. Ignore this question as of now because I didn't teach this solenoid. Or directly you can say in this particular case, this solenoid is basically the coil of many turns. So we have got a coil over, forget about solenoid. We have got a coil over here which has got many turns. This magnet is dropped. We say at the time of entering, we say acceleration is less than G. When it is inside, acceleration will be equal to G. When it is leaving, acceleration will be less than G. Simple, 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 simple. Okay. And when it reaches, when it goes very far, then it will keep on falling with the acceleration due to gravity. That's why I'm saying it is constant. If there is no attraction, no repulsion, it will keep on falling with the same acceleration due to gravity, which is constant. That's why. Now here, if I plot the graph, that is acceleration versus time. At the time of entering, it will face repulsion. So acceleration will decrease. Okay, and when it is inside, then acceleration becomes equal to G. Again, it will increase. And you can see in this particular case, from here to here, it will take some time. Okay, so we say this acceleration remains constant for some time. In the previous graph, again, because when it is leaving, again, I decrease the graph over here. But right now, the acceleration will remain constant for some time. That's why I made the graph something like this. And at the time of leaving, again, acceleration will decrease. Then when it goes far, again, acceleration will increase equal to G. And then it will keep on falling with the acceleration A is equal to G. And this is inside the coil. And this will be at the time of entering. This is at the time of leaving. At the entering. This is leaving. Because at the time of entering, acceleration is less. At the time of leaving, acceleration is less. Guys, tell me in the chats, now is it clear? I hope this is clear now. I hope this is clear now. Because inside the coil, if this magnet has entered the coil, now the coil says magnetic field inside me has now increased. Now let it be. So initially, coil does not want the magnetic field through it should increase or decrease. Now when you have increase, now it says, okay, let it be. That's why we say inside there will be no opposition or repulsion. Okay, great. Now comes the Faraday's law of electro. There are, I think I have solved enough number of questions on Lenz law. Now we have the Faraday's law of electromagnetic induction. We have the Faraday's law of electromagnetic induction. Guys, see. Once again, I'll take the same example over here. Let's suppose I have got a coil. And in this particular case, I'll have a magnet over here. This is the magnet. And because of the magnetic field lines will come out. These are the magnetic field lines coming out of the magnet. We say, if we take magnet close to the coil, magnetic field through the coil will change. If we take magnet away from the coil, we say magnetic field through the coil will change. Again, it will decrease. Previously, it will increase. Now it will decrease. Okay. So we say as whenever magnetic field through the coil, whenever magnetic field through the coil changes, then flux changes. Because we know if magnetic number of field lines through the coil are increasing, flux is increasing. Okay, we say flux changes, and current is induced. Now guys, I would want you to focus exactly over here. And current is induced. So we say whenever the flux or field through the coil increases or decreases, current is induced. So if current is induced in the coil, my dear friends, I would want you guys to answer me one thing. You might have studied Ohm's law. Ohm's law says that V is directly proportional to I. If there is potential difference, there is current. If there is current, there is potential difference or EMF, whatever you say. So here, if current is being induced over here, means potential difference will be there, that is for sure. Because we say current only flows when there is potential difference. So we say as we know, if there is current, it will be because of potential difference or EMF. So means if you are saying by changing the magnetic flux, current is being induced. So basically, if there is current, there is potential difference. So we can conclude by changing the flux, through the coil, EMF is being induced. EMF is being induced in the coil. And this is what we call the Faraday's law of electromagnetic induction, EMI. So whenever the flux through the coil is changed, EMF is being induced. That is what we call the Faraday's law. And it is called Faraday's law. It is called Faraday's law. Okay. So what does Faraday's law say? Now let me write the statement over here. We say, according to Faraday's law, the rate of change of flux, through the coil. Through the coil. The rate of change of flux through the coil. The rate is directly proportional. Directly proportional. Proportional to the EMF induced in the coil. So, by changing the flux, my dear friends, current is being produced. By changing the flux, current is being produced. We say whenever there is flux, there is EMF or potential difference. So, can I say, guys, if you say, I am changing the magnetic field, because of the magnetic field, we say flux is being produced. So if you change magnetic field, flux changes. If flux changes, current is being produced. If current changes, we say EMF will be there. If there is current, there is EMF. So I can directly say by changing the magnetic flux, EMF is being produced. So I can say EMF is equal to, we say, d phi divided by dt. Okay, and you place the negative sign over here. So my dear friends, what is this? This is Faraday's law. We say rate of change of flux through the coil is equal to the EMF induced in the coil. EMF is what? Potential difference. If you change flux through the coil, EMF will be induced. And negative sign is because of the Lenz law, because Lenz law says that the direction of the current will be in such a way so that it opposes the cause. Oppose the cause means if primary magnetic field is increasing, it will oppose it. If it is decreasing, it will support it. Guys, tell me in the chats, is Faraday's law clear? Tell me, guys, is Faraday's law crystalline clear to each and every single student? I would want you guys to give me the signal in the chats. Guys, everyone means everyone. I need the signal from every single student. Is the Faraday's law crystal and clear to each and every single student? Great, great. Now, guys, so we say whenever the flux through the coil changes, EMF is being induced. Now. We say, let's talk about the average EMF, okay, and instantaneous EMF. Guys, see. Let's suppose we have a coil over here. And in this coil, I am saying that we are changing the magnetic field, let's suppose from 9 a.m. to 1 p.m. From 9 a.m. to 1 p.m. From morning to 1 p.m. Continuously, I am changing the magnetic field over here. If you are changing the magnetic field through the coil, we say from 9 a.m. to 1 p.m. continuously EMF will be induced. Okay, because continuously current will be flowing, so EMF will be there. So how much is the EMF created between these two time intervals? How much is the EMF created from 9 a.m. to 1 p.m.? That will be the average EMF. Okay, so it is the EMF. It is the EMF between the time intervals. It is like average velocity, instantaneous velocity. Average velocity, instantaneous velocity. I'll make you understand. See. Guys. I say, if a car moves from this point to this point, sir, how much is the velocity in general from A to B? That is called the average velocity. And what is the velocity at any particular What is the velocity at any particular instant? That is what we call the instantaneous velocity. Okay. So I am saying in this particular case, if the flux through the coil is changing from 9 a.m. to 1 p.m., this is an example between the time intervals. We say in that particular case, we say the EMF developed over here will be average. And when the time is exactly 9:30, how much is the EMF induced? That is the instantaneous. When the time is exactly 10:30, how much is the EMF induced? That is the instantaneous EMF. It is the EMF induced at any particular instant. So I can say this average EMF, I'll write it something like this: average EMF average. It will be simply total change in flux delta phi divided by, we say, delta t. And when it comes to the instantaneous EMF, guys, remember, when it comes to the instantaneous EMF, we say it is the EMF induced at any particular instant. We say it is the EMF induced at any particular instant. Now guys, I would want you to understand, when it comes to the EMF instantaneous, you say that is simply d phi divided by dt. Like you say average velocity delta s by delta t, you say instantaneous velocity ds by dt. Similarly over here. Okay. So average means between the two time intervals, how much is the EMF induced, and instantaneous means at any particular instant, how much is the EMF induced. Okay. Now guys, one more thing I would want you to understand over here. What is that? That is charge or current produced in the coil. Since you know that when flux through the coil changes, current is induced. So can I say as I can write over here, we say as current is equal to, that is V divided by R, because V is equal to IR, I is equal to V by R. And what is this V? V is potential difference, or you say EMF divided by resistance. So in order to find the average current, what will you do? Sir, average current will be simply put the value of average EMF over here. That is delta phi divided by, we say, R, and this will be delta T. And if we talk about the instantaneous current, what is average current? The current produced from 9 a.m. to 1 p.m. What is the instantaneous current? Current produced exactly at 9:30 at any particular instant. So it will be simply, here instead of delta phi by delta t, you will be writing d phi by dt. D phi divided by, we say, R dt. Okay. Where R is the resistance of the coil. R is the resistance of the coil. Okay. You are finding the magnitude over here. That's why I'm ignoring the negative sign. Whenever you find the magnitude, ignore the negative sign. Okay. And I say, if you are saying that, sir, you have got a coil over here, and in this coil you are changing the magnetic field, so current is being produced. So if current is being produced over here, guys, understand one thing. If current is being produced over here, we say it is charge flowing, charge is flowing. So it is charge flowing. So I say charge flown in the coil. Charge flown in the coil. Now guys, tell me one thing. We say we recently saw that as I can say current is simply, that is delta phi divided by R delta T. We got it. But we know as when it comes to the current is simply delta Q divided by delta T. Charge flown upon the time taken. And I can write, instead of this current, I can write over here delta Q divided by delta T will be equal to, that is, will be equal to, then we say delta phi divided by, we say, R delta T. This delta T and delta T will be cancelled. So this delta Q will be delta phi divided by, we say, R. This is the total charge flown in the coil. This is the total charge flown in the coil. Is this clear? Is this clear, guys? Tell me in the chats. So whenever the flux through the coil changes, EMF is being induced, current is produced. I have told you everything. Average EMF, instantaneous EMF, average current, instantaneous current, and charge flown in the coil. Now guys, let's take a look. Let's take a look. Let's take a look. A conducting ring of radius R is placed perpendicularly inside a time varying magnetic field. We have a ring over here. It is placed in the time varying magnetic field. Let's suppose this is a magnetic field, and this magnetic field is given as, that is, we say B naught plus, we say, alpha T, B naught plus alpha T. And in this we have placed a ring over here. In this we have placed a ring over here. Okay. We are supposed to find what will be, and radius of this ring is given as R. What will be the EMF induced in the ring? Guys. Listen to me very carefully. We say here, this magnetic field is changing. So whenever the magnetic field through the ring, through any area changes, we say EMF is induced. And value of the EMF is simply, that is, minus d phi divided by dt. Yes. And what is this phi? Phi is flux. And we can say, sir, this EMF induced here will be minus d by dt of, this is magnetic field into area. Because we say flux is magnetic field into area. Now here magnetic field is equal to, I can say this EMF will be minus d by dt of, what is the magnetic field here given? This is given as B naught plus, we say, alpha T. And what is the area of the ring? Area of the ring is given as pi r square. Okay. And now, guys, in this particular case, we say this pi r square will come out. Pi, this is minus pi r square, because this is constant. Radius of the ring is constant, pi is constant. Now differentiation d by dt of, we say, this B naught plus, we say, alpha T. Now differentiation of this B naught, this which is constant, differentiation of constant is 0, because B naught and alpha are constants. So differentiation of B naught is 0. Differentiation of alpha T will be alpha only with respect to time. So it will be minus pi r square alpha. So this is the value of EMF at any instant. So this is the value of EMF. Let's suppose we have got this question over here. Yes, this is a previous year question. Magnetic flux through a circuit of resistance 20 ohms. Resistance of the coil is given as 20 ohms. We have a coil, its resistance is 20 ohms. Okay. And magnetic flux through a circuit or a coil of resistance 20 ohms is changed from 20 Weber to 40 Weber. So here, in this case, magnetic flux, this is change in flux. Okay. So change in flux, we can write this also, flux final minus flux initial. Okay. So it is changed. So how much will be the change in flux? Guys. So we say it is from 20 Weber to 40 Weber. So I can say that will be 40 minus 20. So change in flux is 20. Okay, in 5 milliseconds. Charge passed through the circuit. We are supposed to find the charge. Guys, tell me one thing. We say as we know, we recently saw that this change in flux, we recently saw that, sir, charge flown delta Q is equal to, we say, change in flux divided by resistance of the coil. You tell me over here, we got it. Charge is resistance of the coil, change in flux divided by resistance. So what is change in flux over here? Sir, that is given as 20. We got a 20. And what is resistance over here? That is 20. So it will come out to be 1 coulomb. The answer of this question is 1 coulomb. Okay. Next. This is the question. Radius of a circular loop placed in a perpendicular uniform magnetic field is increasing at a constant rate R0 meter per second. Guys, see. We say we have got a constant magnetic field over here. This is a constant magnetic field. Okay, this is a constant magnetic field B. And in this constant magnetic field, I am placing, let's suppose, a ring. And its radius is changing, it's increasing, okay? It's becoming bigger. So we say, sure, dr divided by dt is given as R0 meter per second. So radius of this ring is what? I am saying it is increasing. At what rate? We say R0 meter per second, okay? Every second it is increasing by R0. So here radius is changing. And magnetic field is constant. If radius is changing, we say more field lines will cross, so flux will change. So here R is changing. So phi is changing. So phi is changing. Flux is changing. If flux is changing, we say EMF is induced. EMF is induced. So we say EMF is induced. And if you want me to find the EMF in this particular case, we say at any instant when the radius of the loop is R, let's suppose it is increasing, at some instant value of the radius becomes R. We have to find the EMF at that point. Guys, see, we say when it comes to the EMF is minus d phi divided by dt. Tell me one thing. Can I write it something like this? This is minus d by dt of what is phi? That is magnetic field into area. That is d phi by dt, magnetic field into area. So I can write over here, guys, magnetic field is given as B, that is constant. So take this out. So this will be B and then d by dt of this area. And area of the loop, I can say that will be pi r square, because this is a circle, it has got a radius r at some point, so it is pi r square. Now guys, take pi also out because it's also constant, so minus b pi, then it becomes dr square by dt. Now you cannot differentiate r with respect to time. What you are supposed to do, so I would want you guys to multiply with dr and divide with the dr over here. Now change this, interchange the position of dr and dt. Take it over here, take this over here. So you can say this is minus b pi and then I'll write dr square divided by this dr. And when you take it over here, this becomes dr divided by dt. Now you can differentiate this r square with respect to r. Now guys, I can say in this particular case, EMF will be, guys, see, dr square with respect to dr, it will be, what is the differentiation of r square? That is 2r. What is the differentiation of x square? That is 2x with respect to x. So this will be 2r. So it is 2r negative 2r and b pi, and this dr by dt. Don't you think that instead of this dr by dt, we can put up this r0 because it is given as r0 meter per second. So this will be the EMF. Please tell me in the chats if this is crystal and clear. Guys, tell me in the chats if this is crystal and clear, everyone. Tell me in the chats if this is crystalline clear. There is a good question actually over here. In a coil of resistance, 10 ohms, the induced current developed by changing magnetic flux through it is a function of time, okay? The magnitude of change in flux. Okay, guys, okay, very good question actually. See, in this case, current versus time graph is given. We are supposed to find change in flux. Guys, wait. We said to find, we said delta phi, change in flux. Tell me one thing. We recently studied as when it comes to the EMF, okay? Or either you say EMF or you say V, potential difference, EMF, V, it's one and the same thing. We say it is equal to, that is d phi divided by dt. Okay, yes sir. Now can you take it over here? Yes, so I can write this d phi will come out to be, this is v dt. Yes. Now guys, can we say this v, we say v is equal to I into r. Yes, so this d phi will come out to be, we say I into r, and then we say dt. So this is the d phi means small change in flux. To find the large change in flux, we say integrate. So I can do the integration, If you do integration on both sides, so integration of d phi will give you the total change in flux, that is delta phi. And here the resistance is constant, take it out. So it will be r integration of I dt. Now guys, there is a concept which I have taught you in the current electricity. If I am saying I have got the current versus time graph, I and this is T, the graph is this. If you remember over there, my dear friends, the area under this current time graph, this area, the area under current time graph, I told you this area is always equal to integration of I dt. And in case of y versus x graph, it is y versus x. This area under y graph will be simply, integration of whatever is on this axis y, whatever is on this axis dx. Here it is I dt. Now tell me one thing. What is this integration I dt? This is the area of this current versus time graph. So I can write over here, this delta phi will be r, and this is over here area of IT graph. Which IT graph? Now tell me what is the area of this IT graph? Sir, area in this particular case will be area under this line, that is area of triangle, 1 by 2 base into altitude. Base is how much? 0.1. Altitude is how much? That is 4. Now we can write it something like 2 1s are 2 2s are 4. 0.1 we can write as 1 by 10 multiplied by, in this particular case over here, so this will be 2 over here in this particular case. Okay, so I want you guys to 1 by 2 base is given as 0.1. okay, and this will be over here 4. Altitude is 4. 1 by 2 base into altitude. Okay, so this will come out to be 2 1s are 2, 5s are 10. It will come out to be 1 by 5. Now tell me in this particular case, so this delta phi will come out to be this resistance of the coil is given as 10, and area came out to be 1 by 5. 5 1s are 5 2s are, so that is 2 Weber will come out to be the change in flux in this case. Guys, please tell me in the chats if this is crystalline clear. Guys, I would want you guys to give me the signal. Everyone means everyone. Everyone means everyone. Give me the signal in the chats. We'll take the break exactly at 8 o'clock. At 8 o'clock, we'll be taking the break. Not before that. Not before that. Keep that thing in your mind. Now, guys, take a look over here. Magnetic field is increasing with time, then plate of the capacitor, then which plate of the capacitor becomes negatively charged. Guys, see. You have got this region over here. And in this region, inside you have got one, this is the coil, this is the region in which this magnetic field is produced. This is the magnetic field. And this magnetic field is increasing. This B primary over here is increasing. It says that this B primary is increasing. Okay. And inside this you have got a coil in which capacitor is connected. You guys are supposed to tell me which of the two plates will be positively charged. Okay, which plate will be positively charged and which plate will be negatively charged. Okay, see. I would want you guys to focus and listen to me very carefully. See, we say if the primary magnetic field is increasing and it is inwards, Primary magnetic field is increasing and it is inwards, as simple as that. Sir, what about the secondary magnetic field in this loop inside this? We say, sir, secondary magnetic field has to be outwards. Okay. Secondary magnetic field has to be outwards. Okay. So we say in this particular case, secondary has to be outwards. Why? Because we oppose the increasing magnetic field. Sir, that is only possible. If the direction of the current is, we say anti-clockwise, ACW. So we say that is ACW is the direction of the current. Okay. Now, if this is the direction of the current, we say, sir, if the direction of the current is this, means positive charge always flow in the direction of the current. So we say positive will be occupied onto this plate, negative will be occupied onto this plate. Why? Because positive is getting shifted from A to B. It is something like that. Okay. Don't say over here current flows from higher potential to lower potential. No, here current is being produced because of the change in flux. So we say positive charge gets occupied on this plate, negative charge will be occupied on plate A. Why? Because in this particular case, current is flowing in the anti-clockwise direction. So I can say, so it goes from A to B, means positive charge goes from A to B. So here, positive charge flow from A to B. So B is positively charged, A is negatively charged. Tell me in the chats, is this clear? Tell me in the chats, is this clear? Tell me, guys. No. Let's take a look over here. Is this clear? Give me the signal in the chats. Let's take a look over here. Find the time up to which current will be induced in the loop. Find the time up to which current will be induced in the loop. Guys, see. You have got a region over here, and the magnetic field is present in, we say, sir, this B region. Magnetic field is present in the B region. Okay. And I am saying this rectangular loop is moving inside this region. You are supposed to tell me up to which current, up to what time current will be induced. See guys. We say, let's suppose this is the loop. The loop should be bigger than this. Wait, let me find something. Something. Just a second, guys. There is nothing. There is nothing. Guys, see. Let me make the new figure. Then I can make you understand. Otherwise, it is not possible. See? Yeah. So this is B over here. And magnetic field is present in this. Magnetic field is present in this. And you have got a loop over here. This is the loop. It has got the side A. And A is greater than B. A is greater than B. Now, guys, understand this. Understand this. Let's suppose this is the loop over here. Guys. If I say the loop is moving towards this magnetic field, is the current induced in the loop? No, sir. As of now, I am saying no current is induced in the loop. Why? Because no field line is crossing this. No field line is crossing this. No. Now, when it starts entering the loop, now field lines, now it is completely inside. Guys, see, it is completely inside. It is completely inside. Okay. Now again, when it starts going. Okay. Now. Guys, in this particular case, this loop is entering here. See. Please understand. Guys. See, when it is exactly over here, when it is moving inside, current starts flowing, and it is flowing. Till over here, it is crossing how much distance? It is covering how much distance? B. And now, even if you move further, now magnetic field lines will be through it will be constant. Okay. So if I say, sir, no field line is crossing, 1 field lines, 2 field lines, 3, 4, 5. If 5 field lines are now crossing, but still 5, now it will decrease. 4, 3, 2, 1. So when at the time of entering, we say time will be simply. Guys, how to find time? We say, sir, velocity is equal to distance upon or displacement upon, we say time. And if you are supposed to find time is equal to distance upon velocity. Now, how much distance it is covering, till what distance current is being induced? That is B. So that is B divided by, what is the velocity? That is V. This is at the time of entering. Now guys, at the time of leaving, once again, it is covering the same distance B. So we say at the time of leaving, we say time T2 will be again B divided by V. So can I say total time will be, that is T1 plus T2, and that will be 2B divided by V. Don't say 2A by V. It is 2B by V. And when it comes to this question, here, guys, see. In this particular case, let's suppose this is a coil. This coil is entering the magnetic field. Understand this very carefully. This is the coil. This is the smaller. Okay. This coil is smaller than this. Here, the magnetic field is present in this region, that is B. Now, this coil is entering. Guys, understand very carefully. Sir, is there any, right now, is there any current in the coil? No current. Now, when it starts entering, current flows. Yes, till here current flows. Okay, it has covered how much distance? This distance A. Now guys, when it is inside, no current. Why? Because the magnetic field lines through it is constant. Now again, when it comes out, current flows. Sure. Time in this particular case will be T will be A divided by V. T2 will be A divided by V. Total time will be 2A divided by V. Please tell me in the chats how many of you got the feel of these two questions. Tell me. How many of you got the complete feel of these two questions? Is it clear? In that particular case, where A is greater than B, the length of this is greater than this. I know it will be slightly, you will get slightly confused, but later on you watch it once again, it will be clear, that's for sure. So here it will be 2B by B, here it will be 2A by B. Great. Convert the flux time graph into the EMF time graph. We are supposed to convert the flux time graph into the EMF time graph in this particular case. Okay. We are supposed to convert the flux time graph into the EMF time graph. Guys, see. Tell me one thing. We say as. When it comes to the EMF, we say EMF is we say minus d phi divided by dt. Okay. Now, what is this d phi by dt? Guys, take a look at this graph. See. I'll write as in phi t graph. If somebody asks you, what is the value of the slope? When it comes to the flux time graph, if somebody asks you the slope, always remember, we say slope is simply that is d phi divided by dt. If I say you have got y versus x graph. If somebody asks you what is the value of the slope in y versus x graph, you say dy by dx. Whatever is on this axis, dy, whatever is on this axis, dx. Here in case of phi t graph, it is d phi by dt. Now this is equation first and this is equation second. Can you tell me from equation first and second? I can say from first and second. From equation first and second. Guys, see here d phi by dt, here d phi by dt is slope, here d phi by dt is negative of EMF. We can say EMF will be negative of slope. So from now onwards, if flux time graph is given and you are supposed to find the EMF, what will you find? You will find the slope. So slope of slope of phi t graph gives the EMF. Slope of phi t graph gives the EMF. Now, my dear friends, let me draw the EMF time graph. See. Let's take a look over here. So if we have to find the slope, let's suppose this is point A, this is point B, this is C, and this is D. Let's take a look at AB. Guys, when it comes to slope of AB, slope of this curve. Guys, always remember, if theta is less than 90 degrees, if theta is less than 90 degrees, if this theta is less than 90 degrees, means the angle made by the line with the horizontal axis, this, if it is less than 90 degrees, always remember slope is positive. And this is a straight line. In case of the straight line, always remember slope is constant. So here slope is positive and slope is constant. Because why? We say, guys, remember, if for this line theta is less than 90 degrees, we say slope is basically tan theta. So tan of less than 90 is tan 60 is positive. Tan 45 is positive. Tan 30 is positive. All of these values are positive. That's why slope is positive. Now, if slope is positive and constant, can I say from this equation, I can say EMF is equal to negative of slope. We say negative of, what is the value of slope? That will be positive. Whatever it may be, 5, 6, 7, it is positive and is constant. So negative into positive will be negative. So EMF of AB graph will be negative and negative and constant. Let me plot over here for AB graph as of now. So I'll make it over here. So we say in this particular case, this is EMF and this is time. So it says that slope of AB is positive and constant. So I can say it would be something like this. It would be something like this. Okay, so from the upper side the graph is positive, from the lower side the graph is negative, and see, it's a straight line, it is positive. Okay, from A to B. Then when it comes to BC, guys, when it comes to BC, slope of BC, so we say its slope is 0. Why? Because if the line is parallel to x-axis, we say slope will be 0 because it is making the angle 0 degrees over here. So slope will be 0. So if slope is 0, I can say in this particular case, EMF is equal to negative of slope. So we say EMF will be 0. Okay, EMF will be 0. Next we say, let's talk about, okay, now draw the graph. Sir, first you make the graph something like this. Then EMF becomes 0. Okay. So this is from A to B, B to C. Now let's talk about the slope of which one? Slope of CD. Guys, here theta is greater than 90, theta is less than 90. If theta is greater than 90, less than 180, in that case we say slope is negative. We say theta is greater than 90 degrees, theta is less than 90 degrees, less than 180 degrees, like 120, 130, 145. So we say in this case slope is negative. In this case we say slope is negative. And if slope is negative, so we say EMF will be simply negative of slope. And if slope is negative, you can say negative of negative. So it will be positive and it will be constant. Why? Because the graph is a straight line. CD is also a straight line. So it will be positive constant. And then positive constant will be from the upper side. So this will be the graph. Guys, tell me in the chats, is this clear? Is this graph clear? Is this graph clear? Please tell me in the chats. Everyone means everyone. Find the induced EMF in the circular wire. Find the induced EMF in the circular wire. Guys, see. You have got a wire over here, infinite wire in which current is flowing. I is equal to I naught into T square, variable current. At our distance, you have placed this loop over here. You have to find the EMF in the loop. Guys, see. We say magnetic field because of this at our distance will be, I'll write magnetic field due to infinite wire at our distance. I can say this magnetic field will be simply, that is mu naught I divided by 2 pi, we say, sir, R. Okay. Because of an infinite long wire, magnetic field is mu naught I by 2 pi R. Now, what is the current flowing over here in this one? That is I naught into T square. So you can write this will be mu naught I naught T square divided by 2 pi into R. Now, the question in this particular case is, guys, see, I'm saying that what will be the direction of this magnetic field? Place your thumb along direction of current, curl your fingers over here. So it will be inwards. So it is inwards. And this magnetic field is not constant. It is changing. It depends upon time. At t is equal to 1 second, magnetic field will be something. Okay. No. EMF in the circular loop. Circular loop. Sir, why will the EMF be produced? Because whenever the field through the loop changes, EMF will be induced. So we say EMF in this particular case will be minus d phi divided by dt. Minus d phi by dt. EMF in the loop will be minus d phi by dt. Now tell me guys, in this case, can I write it? This will be minus d by dt of. And when it comes to the flux, we say flux will be magnetic field into area. And I can say this EMF will come out to be, that is minus. Then we say d by dt of. What is magnetic field? Magnetic field which is crossing this loop because of that wire will be mu naught I naught into t square divided by, niche se 2 pi r, from the lower side it is 2 pi r, and then when it comes to the area of the loop is simply, area of this loop is simply, that is pi small r square. Now this pi and this pi will cancel out over here, so EMF will come out to be, guys, mu naught I naught will come out because these are constants. Mu naught I naught is also constant, and radius of this circular loop is also constant, so r square will also come out divided by, and here in the denominator you have got 2r and this negative sign, and then what is over here, what remains? So that is dt square divided by dt. What is the differentiation of t square with respect to time? That is 2t. So I can say in this particular case EMF will be minus mu naught I naught r square divided by 2r, and this will be over here 2t. This 2 and 2 will cancel, so in this case this EMF will be minus mu naught I naught r square t divided by, we say, r. Tell me guys, is this clear? Now see, a circular ring of radius r is placed in a magnetic field B is equal to B naught into t square. Is varying. Here magnetic field depends upon time, so it is varying with time. Find the induced EMF at t is equal to 2 seconds. Guys, see, EMF is simply minus d phi divided by dt. And that will be minus d by dt of flux will be magnetic field into area. And I can say this EMF in this case will be minus d by dt of magnetic field into area. What is magnetic field over here? D by dt of magnetic field is B naught into t square. And area of this loop will come out to be, that is pi into capital R square. Now whatever is the constant, take that out. So I can say B naught is constant, so minus B naught, take this out of the differentiation. Pi R square is constant, take this out. Then it remains d by dt of t square divided by over here dt. So I can say this will be minus B naught pi r square. Differentiation of t square will be simply 2t. Okay. Now at t is equal to 2 seconds, it says put the value of at, I say at t is equal to 2 seconds. This EMF will be simply minus B naught pi r square 2 into, we say, sir, 2. It will be minus 4 B naught pi r square. Is this question clear? Is this question clear, guys? If you have not liked this session, and I would want you guys to smash the like button. Find the induced current in the circular loop when key is closed. Guys, always remember, key means this. Right now in this particular circuit, we say current is 0. Why? Because it is not closed. Key is open. Switch is not on over here. So when you switch on, means when you close this key, when you join this circuit, we say current starts flowing. Okay. Right now current is 0. We say when key is closed, remember, when key is closed, current becomes maximum from 0. So when you close this, we say current will increase from 0, it will become maximum. So we say at the time of closing, we say current is increasing. Okay, the current which flows, which leaves this positive terminal and moves over here will increase. So I primary will increase. So I primary will increase. If the primary current increases, my dear friends, tell me, because of this current, tell me, sir, we have placed a circular loop over here. So place your thumb along direction of current, curl your fingers, so it will create the magnetic field over here. That will be outward. This is B primary. Okay. And because of this increasing current, primary magnetic field will be increasing. So B primary is increasing. Okay, and it is outward. Now tell me one thing. When it comes to the increasing magnetic field, don't you think that this coil will oppose the increasing magnetic field? So secondary magnetic field has to be inwards. So I can say B secondary has to be inwards. So that is only possible when the direction of current is clockwise. So my dear friends, when key is closed, at that point of time, you guys are supposed to find the direction of the current in this circuit, in this coil. So that will be clockwise. And my dear friends, when key is open, now current is having some value. If you open the key over here, now don't you think that at that point of time, we say current will become 0. When key is open, then current becomes 0 from maximum. So I can say I primary will decrease. So this is the I primary. So this current will decrease. Because of this current, we say primary magnetic field will decrease. Primary magnetic field will decrease. So because of this, primary magnetic field will decrease. And if primary magnetic field decreases, my dear friends, we know that secondary magnetic field, and it is what? It is outward. Right now also, yes, because the direction of the current will be same from positive terminal to negative terminal. So B secondary right now will be also inwards. Why? Because we support the decreasing magnetic field. So that is only possible if the direction of the current in this particular case is what? Sorry, it has to be outwards. So that is only possible if the direction of the current is anti-clockwise. Curl your fingers along direction of current, thumb is pointing outwards. So we say current will be anti-clockwise. Current will be anti-clockwise. So when key is closed, current is clockwise. When key is open, current is anti-clockwise. This is already done. Let me delete this slide. Let's talk about this. Let's talk about this. See, guys, if magnetic field is continuously increasing, then current flows from A to B. Then current flows from A to B. Is it correct or incorrect? Guys, see, in this particular case, this is the magnetic field. If I say in this case, primary magnetic field is increasing. And it is inwards, You tell me one thing. I'll make you understand. It says that, will the current flow from A to B? I'll tell you. No, current does not flow from A to B. If primary magnetic field is inwards and is increasing, we know, sir, secondary magnetic field has to be outwards. Why? Because primary magnetic field is increasing and that is inwards, because we oppose the increasing magnetic field. So secondary has to be outwards. That is only possible if the direction of the current in the coil is anti-clockwise. Okay? That is only possible if the direction of the current is anti-clockwise. And in this case also, it will be anti-clockwise. Same. So this will be the direction of current. Now, sir, tell me, will this current flow from A to B or B to A? We say here. Remember, here, current does not flow from A to B. This is a conceptual question, from A to B or B to A. Because current always flow in a loop. Okay? So this is a straight wire over here. So current always flow in a loop. If it was something like this, then I would have said, sir, the current would have gone. Let's suppose the current will go something like this and it may flow something like this. Okay? But right now, if I say it was something like this, in this case, I say current will go something like this and it will go something like this. But no. Here it is not forming a loop. In this case, we say current does not flow from A to B or B to A. So I1 will remain. Let's call this as IA and let's call this as IB. We say IA will move in its own loop. IB will move in its own loop. Okay? We say IA and IB will move separately in their loops. Similarly, in this case also, I can say current will be anti-clockwise. In this loop also, current will be anti-clockwise. Like I use the same logic here also, current will be anti-clockwise. This is over here, which one? This is over here, bigger one is, this is IB and this is IA. Simple. Is this question clear? Please tell me in the chats. Tell me, ladies and gentlemen, tell me. Great. Now, in which cases induced current, in which cases induced current is constant in magnitude. In which cases induced current is constant in magnitude? Tell me guys over here. In which cases induced current is constant in magnitude? See guys, in this case, I am saying, you have got this loop over here. It is entering the constant magnetic field. So this is the constant magnetic field present over here. Okay. And in this constant magnetic field, you have got this rectangular loop. This rectangular loop is entering over here. Guys, see, while the rectangular loop is entering, we say number of field lines crossing in 1 second will be same as the number of field lines crossing in second, third second. Why? Because it is uniform. We say in loop 1, I'll write over here. In loop 1, this is the loop 1. In loop 1, we say di by dt is equal to constant. In loop 1, di by dt is equal to constant. Okay. Now, my dear friends, if di by dt is constant, means current is, we say, changing at constant rate. Current is changing at constant rate. So I can say in this particular case, so current in this particular case will be constant. So current in this loop is constant. Why? Because this is a uniform loop, guys. What I'm trying to say in this case is, if the loop is entering the magnetic field, number of field lines crossing the loop in 1 second will be same in the second, third second. So di by dt, change in current, is constant. Okay. We say di by dt in this case is constant. Okay. And if di by dt is constant, we say current is constant. Now, when this loop is entering over here, okay. So we say in this particular case, initially less number of field lines will cross, then more area is entering, more field lines will cross. So we say here in loop 2, I can say di by dt is not constant. So I can say current is not constant. Current will flow, but not constant. Okay. What is Wasim Bhatt doing in the chats? Saving me from the spammers, huh? Yeah, thanks, bro. Thanks. You want something? Yes, we say. It is not MIKE, it is MIC. What is MIKE? Mikey. Give me my Mikey. Take your Mikey. Bro, guys, he gave me the mic yesterday, okay? So this is actually his mic. So thanks for that. He was asking for the money. I told him I'll give you later on. Okay. Now guys, let's take a look over here at this loop 3. Here also in this particular case, I can say current is di by dt is not constant. We say in loop 3, we say di by dt is not constant. If current is not di by dt in this case is not constant, we are supposed to say okay. And here in this particular case, in which of the following case induced current is constant? So I can say in this particular case, current is not constant. So current indirectly, you guys directly write current is constant in the first case. Don't write this di by dt. In loop 1, okay, d phi by dt, it is d phi by dt. d phi by dt is not constant. d phi by dt is constant. Okay, so current is not constant, not di by dt. Okay, it is d phi by dt, d phi by dt. Okay, and here also this d phi by dt, is not constant, so current is not constant. Why? Because d phi by dt is directly proportional to the current. d phi by dt is directly proportional to the current. Okay, in case of this only it will be constant. Here also we say d phi by dt is not constant. We say initially less number of field lines will cross, then more number of field lines will cross. So we say in loop 4, we say d phi by dt is not constant. So I can say current is not constant. Okay. So in this rectangular loop only it will be constant. Okay. So we have 3-4 questions more in this one. So let's take a break, guys. Let's take a break. So I say break till we say 8:45 p.m. So this is a dinner break, long break. And after this break, we are going to finish the session. So guys, let's start again. Now guys, let's take a look over here. Let's take a look over here. Okay. Magnet is draw its acceleration. We are done with this question already. And we are done with this question already. So these two questions we are done with. So let me delete this one and this one over here. So yes, we are deleting. So let's talk about this question. Find the direction of the current. Find the direction of the current in the inner loop. Guys, see in this particular case. We have got the increasing magnetic field over here. Okay. We have got the increasing magnetic field over here. And I am saying that if B primary is increasing, okay, and is outward, simply we say B secondary has to be inward. Okay. So that is only possible if we say direction of the current is this. So this will be B secondary. Okay. So current flows and same will be in this particular case. So this will be over here, the direction of the current in this case, and here also this will be the direction of the current. Simple. Okay. 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 Guys, focus over here. Focus over here. Now see. Let's talk about the motional electromotive force. This is the topic that we are starting right now. That is motional electromotive force. See, or we say motional EMF. Motional EMF. I would want you guys to focus completely over here. Let's suppose I have got a magnetic field over here. This is the magnetic field that I have got. And in this magnetic field, I am placing a conductor over here. There is a conductor which is placed in this magnetic field. Okay. This is the conductor which is placed in this magnetic field. And let's suppose the length of the conductor is L. Length of this conductor is given as L. And this conductor is moving with the velocity V. This conductor is moving with the velocity V. Okay. And it is moving in the magnetic field B. What I'm trying to say is that we have got a magnetic field over here. In this magnetic field, I am placing a conductor. I am placing a rod over here. Okay. Okay. And this rod, this conductor is moving with a velocity V. Its length is L. Since if this is a conductor, we say it will have the charge inside it. It will have the charge over here. Okay. This is the charge inside the conductor. Okay. Now, my dear friends, we know that whenever this conductor flows, whenever this conductor moves in the magnetic field, we say the charge present inside the conductor will also move. Okay. And I can say, I'll write over here, whenever the conductor moves in the external magnetic field, whenever the conductor moves in the external magnetic field. Okay, the charge inside it will experience the force, and that is what we call the magnetic force. Why? Because we have studied previously, whenever the charge is placed in a magnetic field and that charge moves with some velocity, it experiences magnetic force. Okay, we haven't studied this, okay, because we have already only completed half of the magnetism. See guys, simply I'm saying that this conductor carries the charge, and whenever the charge moves inside the magnetic field, it experiences the force acts on it, and that force is called the magnetic force, magnetic force. Okay, guys, I would want you to focus exactly over here. We say what will be and that force will be exactly equal to, that force will be F is equal to, that is QVB sine of theta, QVB sine theta. What I'm trying to say is that if we have got a magnetic field over here, and in this magnetic field you have a charge which is moving with some velocity V, we say, sir, force acts on this. Whenever you place a charge in the magnetic field, force acts on the charge. What is the direction of the force? Place your thumb along the direction of velocity. Guys, remember, place your fingers along the direction of velocity. Curl towards magnetic field. Thumb is pointing upwards. So this will be the direction of magnetic force. Whenever a charge moves inside a magnetic field with some velocity, force acts on it, and the direction of that force is, place your fingers along the direction of velocity. Velocity is forward. Curl towards magnetic field. Thumb gives the direction of magnetic force, that is upward. Okay. Now we say force on this charge will act in the upward direction. This is the force on positive charge. Now don't you think that after some time, guys, understand this very carefully. After some time, we say positive charge gets occupied on the upper side and negative charge gets occupied on the lower side. Why? Because we say if positive charge acts, if force acts on positive charge in the upward direction, it will occupy at the top. Negative charge will be occupied at the bottom. Okay. And here, and this will be upwards. Okay. And what is this theta? Theta is the angle between velocity and magnetic field. Velocity is forward, magnetic field is inward, so theta is 90. So I can say this magnetic force will be, that is QVB. Now guys, tell me one more thing in this case. We say, since positive charge is separated from the negative charge, we say here electric field will be developed. Always remember, whenever you have the positive charge, you have the negative charge. I have told you previously, electric field is always away from the positive charge. Electric field is always towards the negative charge. So here, electric field is from positive to negative. So here, electric field will be from positive to negative charge. Now, electric field is also present. I can say, and positive charge is occupied at the top. Positive charge is occupied at the top. And negative charge is occupied at the bottom. Positive charge is occupied at the top, negative charge is occupied at the bottom. So electric field is set up. Guys, now tell me one thing. We say rest of the charges will be still over there. Okay, some charges have positive charge are occupied at the top, some negative charge at the bottom. Now tell me one thing. Rest of this charge will now experience we say one more force, that is we say electrostatic force. Now we say, now rest of the charge will experience the electrostatic force also. Electrostatic force also. So because of the magnetic field, there is a magnetic force. Okay, I say on this magnetic force is in the upward direction. This is the magnetic force. Okay. And my dear friends, we say because of the electrostatic force will be in the direction of this electric field only. This is the electrostatic force. Okay. Because we have studied, if we have got the electric field over here. In this electric field, I am placing a charge. Force on this charge will be in the same direction of electric field if this is a positive charge. If it is negative charge, force will be in the opposite direction. Here, we say, because of the magnetic field, magnetic force will act, due to which charge gets occupied at the top, positive, negative gets occupied at the bottom. And electric field is set up from positive to negative. Now, when electric field is there, now electrostatic force will also act. Okay. And my dear friends, in this particular case, we say electrostatic force will also act over here on this. Now, this electrostatic force will be equal to, that is Q times of V. Q is the charge. Okay. Q is the charge. And E is the electric field that is set up over here. And my dear friends, we say after some time, after some time, both the forces will be equal. After some time, we say both the forces will be equal. Okay. Now, my dear friends, in this particular case, if both the forces will be equal, so we say this electrostatic force will be equal to the magnetic force. So this electrostatic force is Q times of E. Magnetic force will be equal to, that is QVB. This Q and Q will get cancelled out over here. This is the electric field. E is equal to V into B. Okay, V is the velocity, B is the magnetic field. One more thing I just want to tell you. We know one single thing. Okay. We know as we say a relation between electric field and potential difference, as a relation between electric field and potential difference / EMF. We say this electric field is equal to, that is we say V divided by L, where L is the length of the conductor over here. Okay, where L is the length of the conductor over here. So my dear friends, I can say this V is what? This is EMF. This is EMF divided by L. Now put up over here in this particular case, so I can say this will be EMF divided by L is equal to V into B. So you can say this EMF, guys, this is over here, you can say this is delta V. So this will be, that is BLV. So this is what we call, this is called the motional EMF. This is called the motional EMF. Okay. This is called the motional EMF. Wasim, but your spamming is going to do nothing, okay? Next year also, you will be here. The one who disrespects the teacher is never going to succeed. Keep that thing in your mind. So next year also you'll be here in the same class. If not in this class, you'll be in the another class. That is for sure. Don't expect, okay, whatever the field you are in, you are not going to enter. You are not going to succeed. That's for sure. Keep that thing in your mind. Okay. Now guys, is this clear? Please tell me in the chat. So we say this is the motional EMF. This is the motional EMF. Whenever the rod moves in the magnetic field, whenever the rod moves in the magnetic field with some velocity, whenever the rod moves in a magnetic field with some velocity, we say EMF will be induced in that rod. Okay. And that EMF is what we call the motional EMF. So whenever the rod moves in a magnetic field, whenever a rod moves in a magnetic field, okay, whenever the rod moves in a magnetic field, EMF is induced in that rod called motional EMF. Motional EMF. Is that clear? Come on guys, tell me, is this clear? So basically, this is because of the motion. Okay, this is because of the motion. That's what we call the motional electromotive force. Motional EMF. Now guys, let's talk about the case one over here. See. In this case, magnetic field and velocity are parallel. Means you have got a rod over here. This is the magnetic field. Magnetic field and velocity are parallel to each other. So if the rod is moving something like this, let's find out what is the value of the motional EMF in this particular case. Guys, see. Tell me one thing in this particular case. What is that? I say this V and B are parallel to each other. Okay. Whenever any of the two, like V, B and L, in all of the three, if any of the two are parallel to each other, always remember EMF in that particular case will be zero. EMF in that particular case will be zero. Why? Because we say here I say EMF will be zero. Why? Because guys, when it comes to the force on the charge, we say because magnetic force on the charge is zero. Why? Let me just show you. We say you have this conductor moving in the magnetic field. We say force will act on these charges over here. And what is the value of that force? F is equal to, that is QVB sine of theta. Theta is the angle between velocity and magnetic field. And how much is that? That is zero. So I can say force in this case is zero. If force acting on the charge over here is zero, you tell me one thing. Do you think that charge separation will take place or no? If charge separation does not take place, electric field will set up? No. So if electric field is not set up, we say there will be no EMF. So I can say here, charge separation does not take place. Your charge separation does not take place. Okay. Now. Listen to me very carefully, my dear friends. If I say I have got a magnetic field over here that is inwards, and in this magnetic field you have got this conductor, you have got this wire. This is moving with a velocity v. Here, length and velocity are parallel. Here, we say V and L are parallel. In this case also we say EMF will be 0. Why? Because if any of the two are parallel to each other, we say EMF will be 0. Let me show you how. Guys, in this case, we say this is the charge. Let's find the magnetic force on the charge. We say, sir, that will be V, inward it is B. So direction of magnetic force will be V cross B. That will be something like this. Guys, see, this is the rod. So rod is moving something like this. So V cross B. So force on the charge is upwards, means the charge separation will take place in the width. Is it possible that in this much width, positive and negative charge can be separated? So it is very impossible. It is not possible, sir. Why? Because the width is very small. In length, it is possible. But because, see. I am saying the velocity is forward. Magnetic field is in V cross B. So force on the charge is upward. So positive charge will move upward, negative charge moves downward. Upward means in this width over here. So it is not possible because you write over here, charge separation. Because charge separation does not take place in the width. Okay? If there is no charge separation, there will be no EMF. There will be no electric field, there will be no EMF. Now here in this case, sir, length and magnetic field are parallel. B and L are magnetic field and length are parallel. And in this case, guys, see. If I say this is the charge, this rod is moving in the upward direction, magnetic field is forward. So place your fingers along the direction of current, along direction of velocity. Curl towards magnetic field, thumb is pointing inward. So here also, charge separation will be in the width. Here also, charge separation is not possible in the width. So here EMF will be 0. I say in this case also EMF will be 0. So what I'm trying to say is that, if any of the two are parallel to each other, then EMF will be equal to 0. Keep that thing in your mind. Okay? Then EMF will be equal to 0. Okay? We say all the three, that is B, L and V, should be mutually perpendicular to each other. All the three should be mutually perpendicular to each other. Okay? Is this clear? Please tell me in the chats, guys. Tell me, is this clear? Now, guys, let's suppose we have a question over here. Find the EMF. You have got a rod over here. This rod is making the angle of 60 degrees. Okay. And it is moving with the velocity V. Its length is L. You guys are supposed to find the EMF. Guys, tell me one thing. If this is L, this L will have two components. This will be L cos of 60, because here it is theta, so this will be cos. And this will be, in this case, L sine of 60. This will be L sine of 60. Now you have to find EMF. We say this length is parallel to the velocity. So this will not contribute to EMF. In this case, when it comes to the EMF, we say that will be B, V, and L. Which L? That will be L sine of 60. Why am I taking L sine 60? Because L sine 60, B and V are parallel to each other. See guys, V is in the forward direction. Magnetic field is inward. Okay. And L is in the Y direction. All the three are mutually perpendicular. That's why I'm saying take this L sine 60. And this will be, that is BVL. Sine 60 is a root 3 by 2. So this is basically the EMF in this case. Okay. A rod AB slides on a V-shaped wire. Okay. With a speed V as shown. It is not given. The magnetic field in the region is perpendicular to strength EMF induced. The diagram of the question is not given in this particular case. Let's move on to this one. A thin semicircular conducting ring of radius R. A thin semicircular conducting ring of radius R is falling with its plane vertical in the horizontal magnetic induction B. Okay. Yes. Okay. At the position M and Q, the speed of the ring is V and the potential difference developed across the ring will be. Basically, what the question is trying to say is that, guys, see, I have got a magnetic field over here. This magnetic field is inwards. And in this magnetic field, you have got this structure. This structure, this is a semicircular ring. It is moving with a velocity V. Okay. And it has got a radius of R. You are supposed to tell me what will be the magnetic field. We know whenever the conducting rod moves in a magnetic field, we say EMF will be induced. And how to find that EMF? We say, sir, that EMF will be simply, that is BLV. Now the question here is, what am I supposed to take L over here? Guys, see, whenever you have a structure something like this, whenever you don't have a straight structure, in that case, you join with one end of the structure with another end. This will be at the effective length, L effective. And here you can clearly see that L effective will be 2R. So take the effective length in such structures. So here this EMF will be, that is B, V, and L effective in this case is 2R. So this will be the EMF induced in the wire, something like this. Okay. Let's suppose you have a question something like this. Guys, here, I'm saying EMF in this case will be, whenever you have a structure something like this, we say, you don't have to take this length, guys, you have to take the L effective. Here L effective is equal to 2R. Now you tell me one thing. Don't you think that L effective and V are parallel to each other? Okay. So L effective and V are parallel to each other in this case. We say L effective and V are parallel to in this case. No. We don't have to take this. We don't have to take this. Guys. We don't have to take this. We have to take the L effective. Join the initial point with the final point. That will be the L effective only. Okay. And now. See. In this case, L effective and V are parallel. L effective and V are parallel. So what will be the value of EMF? 0. Because I have told you, if any of the two are parallel to each other, we say in that case EMF will be 0. Okay. Let's talk about this one. You have got a frame structure over here. Okay. And here magnetic field, this is a kind of circuit. Magnetic field is inward This is the inward magnetic field B. Resistance R is connected. And you have this wire which is slidable on this structure. You have this wire which is slidable on the structure. You guys are supposed to find the power delivered in the circuit. Okay, guys, see. This is the structure. You have this conductor connected over here. This conductor can be slided over here. So means it is moving back and forward and backward. And in this case, you guys are supposed to find out the power. I can simply say here power is V square divided by R. Your power is V square divided by R. And my dear friends, in this particular case, I can say this power will be, okay? I can say this power will be, what is V? V will be in this particular case, that is EMF, that is potential difference divided by R. EMF square divided by R. EMF square divided by R. R is the resistance. Now, my dear friends, I can say this power in this case will be, what is the EMF in this particular circuit? We know, whenever the rod moves in the magnetic field, we say EMF will be induced. And that EMF in this particular case will be simply, that is BLV. And I can say over here, this will be, that is BLV, and it is whole square divided by R. And this power will be, what is the value of magnetic field? Now see, all the details are given over here. So strength of the magnetic field is 1 Tesla. So this is given as 1. What is the value of the length? Length of the rod is given as 1 meters. What is the value of the velocity? That is 20. So it will be 20, and this is whole square divided by. What is the resistance? Resistance is given as 0.2 ohms. Resistance is given as 0.2 ohms. Okay. Now, this will be basically, that is how much? 20 square is, we say, sir, 400 divided by 0.2. That will be 2 by 10. So this will come out to be, that is 4000 watts over here. Okay. Is that clear? Guys, tell me in the chats. I would want you guys to let me know in the chats if everything is crystalline clear. Okay. Tell me, guys. Everyone means everyone. Okay. Oh, so 400, this will be 4000 divided by 2 over here. So that will be 2000 watts. That will be 2000. Okay. Great. Or we say 2 kilowatt. Yes. Now, guys, let's talk about this structure. Find the EMF induced in the square loop. Find the EMF induced in the square loop. Find the EMF induced in the square loop. See, guys, you have got a square loop over here. When it comes to the EMF in this particular case, let's take a look exactly at this thing. See. We say this rod is moving in the forward direction with the velocity V. Okay, the structure is moving with a velocity V. And this is made up of 4 wires. Let's find the EMF individually over here. Let's talk about first which one? Sir, AB and CD. Don't you think that this AB and CD are parallel to velocity? So I can say EMF in, we say, AB will be equal to 0. And then we say EMF in CD will be equal to 0. Why? Because these two are parallel to the velocity over here. As simple as that. Now, EMF in this rod, EMF in this rod. So we say EMF in, we say AC. EMF in, we say AC will be, sir, magnetic field is given as B, length side is given as L, and velocity is V, that is BLV. And EMF in this BD, we say EMF in this BD is also given as, that is BLV. That is also BLV. Okay. 20-30 slides or more, bus. That's it. We are done. 30 more slides and we are done. Okay. Now see. Now let's suppose, my dear friends, you are saying that one more thing I forgot to tell you. That is, if I say you have got a magnetic field over here. In this magnetic field, this wire is having length L. It is moving with a velocity V. Magnetic field is B. We say EMF will be induced. And we know EMF is in case of the battery. Battery is having the EMF. So you can say, sir, this has the EMF of BLV. Now, whenever we talk about the battery, it has got the positive terminal, it has got the negative terminal. Here, sir, if it resembles with a battery, if it will behave like a battery, could you please make its positive and negative terminal? See, whatever is the direction of the positive charge, whatever is the direction of the force of positive charge, same will be the positive terminal. Guys, how to find the direction on positive charge? Place your fingers along direction of velocity, curl towards magnetic field. Thumb gives you the direction of force on positive charge, so that is upward. So this will be the positive terminal, because positive charge will be developed, will be occupied at the top, and negative charge will be occupied at the bottom. So this is positive and this is negative. This is positive, this is negative. Why? Because the direction of force on positive charge is from the higher side. Okay. Now guys, listen to me very carefully. Listen to me very carefully. Listen to me very carefully. We have got a structure over here. You can exactly see in this particular case. Okay. We have got a structure, you can see exactly in this particular case. And you guys are supposed to tell me what is the potential difference between B and D. What is the potential difference between this B point and D point? Means EMF you guys are supposed to find out. Now see. If I say in this particular case, okay. In this particular case, we said the structure is made up of two parts. The structure is made up of two parts. This is the first part over here. This is the first part over here. The structure is made up of two parts. This is the first part. And this is the second part over here. This is the second part over here. Now guys, this is given as 2R. So means this radius will be also 2R over here. So this will be also 2R over here. If I ask you, what is the effective length of this part? You say, sir, this will be 4R. 2R plus 2R is 4R. What is the effective length of this structure? This will be also 4R. Now, guys, I would want you to focus. We say, in this part also EMF will be induced. In this part also EMF will be induced. How much is the EMF in this induced in this part? It is moving with a velocity v. How much is the EMF induced in this part? You say, sir, EMF here will be, you have to take the effective length I told you in case of the structures like this. So that will be magnetic field is B, velocity is V, L effective is 4R. And here also we say EMF will be, that is B, V, and then we say 4R. Okay, B, V, and 4R. No. Let's suppose you have to tell me, you have to make the battery. You have to make the battery. Instead of this, make a battery over here. Guys, tell me, this is the velocity and magnetic field is inward. Magnetic field is inward. So place your fingers along direction of velocity, curl towards magnetic field. Thumb is pointing downwards. So this will be the positive terminal. This will be the negative terminal from the upper side. Similarly, in this particular case, I can say this will be the negative terminal, this will be the positive terminal. Okay, so I say over here, this will have that is BV4R, and this will have that is BV, and I say this is 4R. BV4R, and this is BV4R. Now, guys, tell me one thing. This is the EMF. This is the EMF of this structure. Could you please tell me what will be the net EMF in the entire loop? We say EMF in the loop net will be equal to 0. Why? Let's suppose you start from this point A. I have told you in the current electricity chapter how you guys are supposed to write the potential difference. You guys start from A. We say select the path. So first, if you are starting from A, you write the potential of A. Then in case of the battery, if you go from lower potential to higher potential, you take this as, we say plus BV4R. Guys, remember, do you guys remember when we used to move from point A to point B? Point A to point B. We say we first write the potential of that point. Then in case of the battery, if you are moving from lower to higher, you take its drop as positive. And from higher to lower, you are taking its drop as negative. That is BV4R is equal to, we say, sir, VB. Now in this case, we say this EMF net will come out to be 0. This will cancel with this one, this and this. Not VB, it will again reach directly VA. Because we are moving in a closed loop. So we say net EMF is 0. Guys, tell me, is this clear? Please tell me in the chats, is this net EMF clear over here? Tell me. No, you don't have to consider this smaller circle. You have to consider this part also from here to here, from B to D. That's why. Potential difference means EMF itself. Either you say potential difference, across this point and this point, or you say EMF. That's one and the same thing. In this particular case, okay, this is actually a good question. See guys. I am not taking, guys, don't get confused over here. You don't have to consider this as the second. No. It is a wire. This is a complete, the structure is this one. This is the structure. So here I am saying the structure is made up of two parts. First is this part. This is the first, and second is this. Why should I take this one only? I'm supposed to take from here to here. This will be the effective length. It's not like you have to take the two semicircles over here. No. See, let's take a look at this question. In this particular case, it says that a PQ rod of 5 meter oriented as shown in the figure is moving with a velocity 2 cap. Velocity in this case is given as 2 cap meter per second. Without any rotation in the uniform magnetic field. So magnetic field in this case is given as, that is 3 cap plus 4 k cap Tesla. The EMF induced in the rod will be, we are supposed to find the EMF. Guys, see. Let's first find out the length. Let's suppose this is the length of the rod. Okay, that is given as 5 meters. This is 5. Don't you think that this component will be, that is 5 cos of 53 degrees. And this component will be, that is 5 sine of 53 degrees. Now tell me in this particular case, sir, this is 5 sine of 53 degrees. This is 5 cos of 53 degrees in this case over here. Okay. Now, if I ask you, what is the value of this 53 degrees? Guys, understand this very carefully. We say, this is a triangle. I have told you this so many times. 53-degree triangle and 37-degree triangle. So we say this is 53 degrees and this is a 37-degree triangle. Remember from now onwards. If this is 53 degrees, this side will be 4, this will be 3 and this will be 5. If this side is 37, this will be 3, this is 4 and this is 5. Hypotenuse in both is same, but here in front of the bigger angle, you have got the bigger side. In front of the smaller angle, you have got the smaller side. 337, 453, 3, 4. Now, sure, if I ask you what is the value of cos 53, that is base by hypotenuse. So cos 53 will be simply, that is 5 into cos 53 is 3 by 5. 3 by 5. So this and this will cancel. So this will be 3 and I'll write I cap. What does this I cap actually mean? I cap means the direction of the vector is along positive axis. See, this is along positive axis. That is why I'm mentioning I cap. And here, if I ask you what is the value of 5 sine 53, you say, sir, 5 sine 53 is perpendicular upon hypotenuse, that is 4 by 5. 4 by 5. 5 cancels. So this will be 4j cap. 4j cap. Sir, why 4j cap? J cap means this vector is along y-axis. Now, if I write this length over here, length vector, that will be, we say 3I cap plus, we say, sir, 4j cap. One component is along x-axis, another component is along y-axis. So this is length, magnetic field, velocity. You have to find the EMF. Guys. We say, if any of the two components are parallel to each other, okay, then we say EMF will come out to be 0. Now, my dear friends, in this case, velocity is in the x-axis. Magnetic field is in the x-axis as well as z-axis, because k cap means the direction of magnetic field is z as well as x, I and k. And here, understand one thing. And this length is in the x and this is y. Now tell me one thing. Guys, if I take velocity is in the x direction, take this component of the velocity only, because you have got only x component, take x. Now, if you take, in case of magnetic field, if you take 3I cap, then sir, this magnetic field and velocity becomes parallel, EMF will come out to be 0. So we have to take, sir, magnetic field in K cap, magnetic field K. Guys, X means X direction. K means Z direction, means they are parallel, they are perpendicular. And then when it comes to the length you have to take Y. X, Y, Z. X, Y, Z, and this is in the Z, this is in the Z. Now tell me, in this particular case, I can say in this particular case, this will be the EMF over here. Sir, why did I take this? Why did I take this over here? Why did I take this over here? Because all the three should come out to be mutually perpendicular to each other. If I take this 3I and 3I, they are parallel, so EMF will come out to be 0 in this case. Okay? Okay? Guys, tell me, is this clear? Now, how much is the value? How much is the value? What is the Vx component? Sir, velocity in x direction, that is given as 2. Sir, magnetic field in z direction, you have to take 4 over here. Not I cap, but 4. And length in y direction, you guys are supposed to take as 4. 4 into 4 is 16. 16 into 2 is, we say 32 volts. 32 is the answer. Give me the signal in the chats. How many of you understood this? Tell me, guys. See, I'll explain once again. I'm saying velocity is in the x direction. Cool? Yes. Magnetic field is in x direction as well as z direction. Okay? Okay? It would be something like this. X as well as z. This is the x axis, this is z axis, so it will be something like this. Length is in the x direction and y direction. Now here, if you want to find the EMF, we know EMF is BLV, and all the three should be mutually perpendicular to each other. How you can take over here the components of BL and V so that they should be mutually perpendicular? I'll take velocity in x direction because I cap means x direction, because there is only I cap, so I'll take in I cap direction. So velocity in x is given as 2. Sir, in case of magnetic field, shall I take the x component or z component? You tell me. Sir, I'll take x component. If you take this x, velocity is already in x, so they become parallel, so EMF will be 0. So you have to take this. So that's why you have to say this EMF will be, velocity will be in x direction, x component of the velocity, and here z component of the magnetic field, and then sir, I'll take x component of this length. Already velocity is in x, they become parallel, EMF will be 0. So I have to take that is y component. Sir, it is 3j cap. Sine 53. Okay, sine 53 is perpendicular upon hypotenuse. Okay, that is 4 by 5. 4 by 5. 5 and 5 will cancel, so 4 remains. Where are you saying it is 3j cap? Okay, it is 3j cap over here. Okay, it is 3j cap over here. Okay. Okay. Even if it is 3j over here, still I cannot take this 3j cap over here. Okay. Okay. 3j plus 4k. Still I'll have to take 4k over here because in this case I cannot take x and I'll have to take this y because x already I have taken in this one. So answer will still be 32. Answer will still be 32. Answer will still be 32. Guys, do watch it later on once again. It is not that difficult question. Let's suppose you have a question something like this. Magnetic field is uniform over here. Okay. Magnetic field is uniform over here. In this particular case, you guys are supposed to tell me the EMF induced. In case of the structure, something like this, I told you take the effective length. So this will be the L effective. Now guys, tell me one thing. If I say EMF in this case, guys, understand very carefully. This is L. This is V. This is magnetic field B. Now, we say all the three should be mutually perpendicular to each other. All the three should be mutually perpendicular to each other. If this is L effective, don't you think that one of its components is this? This is the radius R. Another component is this. Okay, one component, another component. Guys, it is a vector. One component is this, another component is this. Now, this component is parallel to velocity, so it will create zero EMF. This component is perpendicular to velocity and magnetic field. This is in the y direction, velocity in the x, and outward is the magnetic field. So here EMF will be B, and you don't have to take L effective over here, because you have to take that component of L effective which makes 90 degrees. That is this BR, BL, VV is the velocity. So this will be the EMF in this case. Is that clear? Is that clear, guys? Let's take a look at this question. Let's take a look at this question. Guys, tell me, if you have a structure something like this, you have to find the EMF. What do? Sir, we take the effective length. So this will be the effective length over here. This will be the effective length over here. Okay. And guys, tell me one thing. If this is L, so if I resolve this in two components, this will be 60 degrees. This will be 60 degrees. Guys, this is L. Which component is this? Will be L cos 60. This component will be L sin 60. This is also L. If this is L, this is 60. This component will be L cos 60. This will be L sin of 60. L cos 60, L sin 60 plus L sin 60. Now tell me in this case, from A to B, A to C, what will be the effective length? I can say here L effective is simply, that is 2L sine of 60 degrees. This will be the effective length in this case. And when you are supposed to find the EMF, that is BVL effective. So that is magnetic field is B, velocity is V. L effective is 2L sine of 60 degrees. So that is BV. 2L sine 60 is root 3 by 2. So this and this will cancel. So this will be a root 3 BLV. Root 3 BLV is the correct answer. Let's move on to this one. Find the current in the rod. Guys, tell me one thing. You have got the resistance. Let's call this as R1 is equal to R and R2 is equal to R. You have got the two resistors in the circuit over here. And then there is a rod placed in between which is sliding. This rod can be sliding over here. It is moving with the velocity V. Its length is L. And it is placed in the magnetic field B. You guys are supposed to tell me the current in the circuit. First of all, if the rod moves in the magnetic field, EMF will be induced. What will be the EMF in the rod? Guys, tell me one thing. Can I say in this particular case, instead of this rod, I'll make a battery over here. And then this resistance, that is R. And from this side, this resistance, that is also R. This is also R. And guys, this will be having the EMF is equal to BLV. And sir, in this particular case, you are supposed to make the positive terminal from the upper side. Because place your fingers along direction of velocity, curl towards magnetic field, thumb is pointing upwards. So this will be in the, so this will be somewhere around over here. So this is positive, this is negative. Now tell me guys, in this case, I can say current will be simply, that is V by R, or EMF divided by R is the resistance, and R equivalent. Tell me one thing, how much is the EMF of this battery? That is BLV, that is BLV divided by R equivalent. Now, what is the equivalent resistance over here? This is R, this is R. Whenever two resistors are in parallel, their equivalent resistances, we say, sir, R equivalent in that case will be R1 R2 upon R1 plus R2. And this is R1 R2 is R and R, that is R square, divided by R plus R is 2R. This and this will cancel, so it will be R by 2. So this current in the circuit will be, that is BLV divided by R by 2. So that is 2 BLV divided by R. So simply I'm saying, if you have got a rod which is sliding, it will create EMF. It will behave like a battery and it will have the EMF E. Now this becomes the question of current or electricity. So I say I is equal to V by R. Guys, is this clear? Tell me in the chats. I need the signal from every single student. Whosoever is watching, I need the signal. No, current electricity is not the basics of this chapter. No. The basics of this chapter is magnetism. Now see, find the EMF in the rod, in this rod. Guys, tell me one thing. There is an infinitely long wire. Because of this infinitely long wire, magnetic field will be produced over here. Place your thumb along direction of current. Magnetic field is over here. So we say this is the magnetic field inwards. Okay. And here this is the magnetic field inwards. Because of this wire, magnetic field will be present at a distance. And in that magnetic field, this rod is moving with a velocity v. Now, how much is the EMF over here? We say EMF is equal to, that is BLV. And what is the magnetic field because of this infinitely long wire? Mu naught I divided by 2 pi R. R will be over here A, at A distance. So I can say, sir, magnetic field will be, that is mu naught I divided by 2 pi A. And velocity is V, length is L. L is the length, V is the velocity. This will be the magnetic field. This will be the magnetic field. This will be the magnetic field. This will be the EMF in the rod. This will be the EMF in the rod. Now, here. Guys, in this case, length and velocity are parallel. So here EMF is 0. EMF is 0 because length and velocity are parallel. If any of the two are parallel to each other, then EMF will be 0. Let's talk about this one. If you have got an infinitely long wire, this is an infinitely long wire. Okay. and we say at a distance, just a second, I'll make it properly over here. Yes. Now guys, I'm saying in this particular case, this from here to here, this is A. Length is L. Current in this is I. It is moving with the velocity V. I say find the EMF induced in the rod. Find the EMF induced in the rod. You guys are supposed to tell me EMF induced in the rod. See guys, in this case, I would want you to focus. We say, sir, because of this wire, magnetic field will be present over here, and that magnetic field B will be inwards. But this magnetic field is different at different points. If you go away from the wire, magnetic field will decrease, it will change. So you cannot directly use EMF is equal to BLV over here. We say here EMF, here magnetic field due to the wire is variable. Okay, because at a distance magnetic field is mu naught I by 2 pi a. At this distance it is mu naught I by 2 pi a plus something. At this distance magnetic field is something else. Okay, it is different. Sir, what about this case? Here at a distance, because the rod is placed over here vertically, so at this a distance magnetic field will be constant. But if you take it at somewhere else, then the magnetic field will be different. But at this distance it is constant. But in this question, at this distance magnetic field is something. Horizontally magnetic field is different. Now, let's suppose we'll take a small strip over here. Let's find the EMF in this small strip over here. Let's take a small strip. Which is at what distance? Which is at x distance. And the width of this is, we say, sir, dx. Okay. I'll write over here. Let's take a small strip. Let's take a small strip of dx length. Okay. Magnetic field at x distance. Guys, see, this magnetic field will be simply, that is mu naught I divided by 2 pi x. So because of this wire, at x distance mu naught magnetic field will be mu naught I by 2 pi x. Now guys, tell me one thing. In this magnetic field, we said this strip is basically moving with a velocity v. It has got how much width? That is, we say, sir, dx. L is the length. Now, EMF induced in the small strip. Whenever you have got the varying magnetic field, in that case, you guys are supposed to take the small strip. So EMF in the small strip will be simply, that is d phi. Sorry, that is dE. Okay. So it will be equal to BLV. Sir, what is in this particular case? What is, we say, magnetic field B? That is B length is L, V is velocity. So what is the magnetic field? So that is, we recently got, that is mu naught I divided by 2 pi x. And what is the length of this strip? That is given as dx. And what is the velocity? That is v. So this is dE. And if I ask you to find the total magnetic field, to find the net magnetic field, so we say this will be integration of dE, and this will be equals to integration of mu naught I divided by 2 pi x, and then we say dx into, we say, sir, b. So this is basically the EMF induced in the small strip. If you want to find the EMF in the entire rod, so you'll have to integrate it from A, because from here to here it is A. So here the distance is A plus L, because this length is L. So you integrate it from A to A plus L. And then this EMF will be equal to EMF net is equal. So mu naught I, take it out because this is constant. So mu naught I into V. V is also velocity is constant, divided by 2 pi. And then it will be integration of 1 by x. We say from A to A plus L. From A to A plus L. Okay. Now guys, in this particular case, you can say this EMF will be, that is mu naught IV divided by 2 pi. Integration of 1 by x will be ln of x. And limits are from A to A plus L. So then you can write this EMF will be finally, that is mu naught IV divided by 2 pi. And then we say ln of, in this x, you put first the upper limit, that is A plus L divided by A. Guys, please tell me in the chats how many of you understood this properly, clearly, each and every single thing. Tell me. Why V is not differentiated? Because velocity is constant. It will take us next 1 to 1.5 hours, because we are already done with the 78 slides, and we have a total of 85 slides. Okay. Now guys, see. Yeah. Many topics are pending. Is it fine now? Is it fine now? Yeah. Now guys, let's take a look over here. Self-induction. Self-induction. Let's suppose we have a coil over here. This is a coil of many turns. This is a coil of n turns. This is a coil of n turns. Okay. This is a coil of n turns. And in this coil, I'm saying current I is flowing. Current I is flowing. Okay. I'm saying current I is flowing. Now, whenever this current I flows in the coil, whenever this current I flows in the coil, we say magnetic field is being produced. We say due to the current, we say flux is produced. Guys, whenever the current flows in the coil, I have told you previously, let's suppose this is a coil. In this coil, current I is flowing. Because of this current, magnetic field will be produced. Curl your fingers along direction of current, thumb will be inwards. This is the direction of magnetic field. Now, if I place the coil something like this, I say current is flowing in the coil, okay? Now, curl your fingers along the direction of current, thumb is pointing something like this. So, this will be the magnetic field, this will be the magnetic field, this will be the magnetic field, okay? And this magnetic field is crossing the area of the coil. And I'm saying magnetic, if it is crossing, so flux is produced. Now, if I say, more is the current flowing over here, we say more will be the magnetic field produced, more will be the flux. So can I say here, so I can say magnetic field, this magnetic flux is directly proportional to the current. More is the current, more will be the magnetic field, more will be the flux. So flux is directly proportional to the current. Now replace this with a replace this proportionality with a constant. We say replacing proportionality with a constant, So I can say this phi will be equal to L into I. This phi will be equal to L into I. And what is this L? L is what we call where L is called the self-inductance. L is a constant where L is called the self-inductance. Where L is called the self-inductance. Like guys, in case of Ohm's law, we say V is directly proportional to I. And replace this with a constant V is equal to R into I, where R is the resistance of the material. Similarly, L is what we call the self-inductance. Like you say, sir, Q is directly proportional to V. Charge on a capacitor is directly proportional to the potential. So replace the proportionality with C. So C is what we call the capacitance of the capacitor. Similarly, L is called the self-inductance of the capacitor. Then you further write this resistance is rho L by A. Similarly, here we say this L is equal to, that is mu naught N square A into L. This is the value of this self-inductance. Like you say, resistance is rho L by A. Length of the conductor, area of the cross section, resistivity. This is equal to mu naught N square A into L. Mu naught is permeability of free space. N square, we say this N is number of turns. per unit length. Per unit length. Okay. And we say A is the area of cross section. Area of cross section. A is the area of cross section. And we say L is the length of the conductor. L is the length of the conductor. Okay, we say L is the length of the conductor. Now guys, no, not the conductor, inductor of the coil. Of the coil. Now, I would want you to focus. Let's suppose if I say current in this coil is changing. We say if the current in the coil is changing. If I say current in the coil is changing, we say because of the changing or increasing current, magnetic field will increase. Because of the increasing magnetic field, flux will increase or flux will change. So we say if the current in the coil is changing, we say then flux will also change. Now tell me one thing, my dear friends. How do you write this change in current? If the current is changing, how do you write change in current, sir? Change in current will be di by dt. Okay, L you keep it as it is. Why? Because self-inductance is constant. It will not change, is equal. Because of the change in current, flux will change. So how do we write the change in flux? So d phi divided by dt. Now, whenever the flux through the coil changes, that will EMF will be induced. We say we say EMF is equal to d phi by dt. Okay. So instead of this d phi by dt, you can write, sir, this EMF, negative of EMF. So put the negative sign over here. This is L di by dt. So my dear friends, what is this? This is what we call the EMF induced in the coil. So guys, focus. We say EMF induced in the coil. If the current in this coil is changing, we say EMF is induced in the same coil. This process is what we call the self-induction. Creating the EMF in the same coil is what we call the self-induction. Okay, this process, we say this process of creating EMF in the coil is called self-induction. Sir, then what is the mutual induction? Mutual induction will be if the coil in the circuit is changed, if the current in one coil is changing and EMF is induced in another coil, that is mutual. But when it comes to the self-induction means if the current is changing in this coil, EMF is induced in the same coil. So we say the process is what we call the self-induction. And this N is the number of turns per unit length, means how many number of turns are on the unit length. It is not the total number of turns. Okay. In this case, the direction of magnetic field is, guys, this is the coil. Curl your fingers along direction of current. Thumb will be like this. So like this, along the axis. So this will be the direction. So this is what we call the self-induction. Now guys see. Now guys see. Understand one thing very carefully. Understand one thing very carefully. Case 1. Case 1. If the primary current, is increasing, see guys, let's suppose I have got a coil over here, and I am saying that in this coil the current which is flowing, this I primary, this is increasing. We know that according to the Lenz law, if the current in the coil is increasing, okay, if the current in the coil is increasing, we say, if you have got a coil over here, if the current in the coil is increasing and EMF, we know that according to the Lenz law, this coil will oppose the primary current. So basically what I'm trying to say is that if this is the direction of the primary current, we say the secondary current will be induced in this coil. Sir, you are confusing us. I know. Wait. I'm saying because of this primary current, magnetic field will be induced. And if magnetic field in the coil is induced, understand one thing, because of that magnetic field, we say that magnetic field will change through the coil. That magnetic field, I'm saying, let's suppose guys, this is the coil over here. If primary coil in the coil, this is the primary current. Because of the primary current, this will be the primary magnetic field. And if this primary magnetic field is increasing, we say flux will be increasing, changing. If flux in the coil is changing, we know whenever the flux changes in the coil, current is induced. We say in this coil, another current will be induced. That is called the secondary current. And the second direction of the secondary current will be in such a way, it's so that it opposes the increasing current. Now guys, I am saying, what I'm trying to say in this case is, we say, because of the primary current, okay, because of the primary current, magnetic field is induced. Because of the primary magnetic field, flux is induced. If this is changing, this will change. If this will change, I secondary will be induced. Now the direction of this I secondary is, if primary is increasing, it will oppose the increasing current, because Lenz law has told us. So if this is in this side, so this will be the direction of the secondary current. Okay, we say I secondary will oppose the increasing current. Okay, and one more thing, we say I secondary will support the decreasing current. Now guys, let's suppose I say I have got an inductor over here. Okay, and in this inductor, I am saying this is the primary current, I primary, and this primary current is decreasing. Primary current over here is decreasing. Okay, this is the primary current which is decreasing. Now in this case, we say, sir, induced current in this will be developed. Okay, this will be I secondary. It will support the primary current. And now, if you want to make the battery, because instead of this, if you want to make the battery, guys, see, you'll be making it something like this. This will be the positive terminal. From this side, it is negative terminal. Because if you make the positive terminal from this side, then only current will be, the direction of the secondary current will be towards this. Because secondary, this current always leave from the positive terminal. because current always leave from the positive terminal. Okay, and here, if you want to make the battery in this particular case, so we say it will be something like this. This will be the positive terminal. Then only the direction of the current secondary will be this. And what is the EMF? What is the EMF in this particular case? So EMF of this battery will be simply, that is L di divided by dt. That is what we have discussed. What I'm trying to say in this case is, if the current in the primary coil is increasing, magnetic field will increase. Because of that, flux will increase. If flux through the coil is changing, Faraday say that current will be induced. That current will be secondary current. And what will be the direction of secondary current? Secondary current will oppose the primary current. If primary current is increasing, if this is the direction of increasing current, secondary current will oppose it in this direction. So it is only possible if you make the positive terminal from this side, then only it will leave the current, the current will come out of the positive terminal in this direction. Similarly, in this case, here we say current is decreasing primary. So secondary current will support the decreasing current. That is only possible if you make the positive terminal from this side. Guys, please tell me in the chats, please tell. We don't have to discuss that, will they cancel out, will they add up? No, we just have to, in this chapter, we only talk about support and oppose, support and oppose. That's it, that's it. Is this clear? I need the signal from every single student, whosoever is watching. Let's take a look over here. The current passing through a coil of 500 is decreasing at a rate of 2 ampere per second. Guys, it says that we have got a coil over here. In this coil, current is decreasing, means di by dt. So this is what we call the change in current. Di by dt is given as minus 2 ampere per second. Okay, means current is decreasing at a rate of 2 ampere per second, means every second it is decreasing by 2 ampere, 2 ampere, 2 ampere. And the EMF developed across the and inductance of this is given as, that is 500. We are supposed to find the EMF is developed across this coil, because we recently studied whenever the current through the coil changes, we say EMF will be induced. And my dear friends, how to find the EMF? EMF will be simply, that is L di divided by dt. You say minus L di by dt. And we say this EMF in this case will be minus, what is the value of L? That is 5. And what is di by dt over here? That is minus 2 ampere per second, because it is decreasing, that's why minus 2. So 5 into 2 is 10, minus into minus is plus, so we say plus 10 volts. Plus 10 volts. Okay. If number of turns in a coil is doubled, without any change in its length of the coil, okay, without any change in its length of the coil, its self-inductance becomes. I would want you guys to answer this particular question. What is the option in this case? Which option is correct in this case? Tell me. Tell me. Why option A? Why are you saying option A? See guys, if number of turns in a coil is doubled without any change in its length, its self-inductance becomes. See guys, we say as. When it comes to the self-inductance, it is mu naught n square A into L. Okay. It says that, sir, this length over here is constant and we are assuming area is constant also. Mu naught is constant. And my dear friends, we say L is proportional to over here n square. L is proportional to n square. Okay. And if L is proportional to n square, means if number of turns is doubled, L becomes 4 times. So we say option A. Okay. And let's take a look. Here it says that a long solenoid of inductance L, if its length is doubled, keeping the total number of turns constant. See guys, we say as self-inductor. I hope this is clear. So number of turns here is given. So means all rest of the things are constant. L is proportional to n square. Means in case of an inductor, it says that if you double the value of n, number of turns per unit length. Guys, I am saying that you have got an inductor over here. If you are doubling this n, okay, let's suppose if it was previously n, you are making it double over here. So means 2 square will be equal to, if initially it was 1, now you are doubling it, making 2. So it is n square. 2 square will be equal to 4. So L will be equal to 4. Because L is equal to n square. Now if it is doubled, so that will be 2 square. So it will be 4 times. That's what I'm saying. It will be 4 times. And now see over here, it says that a long solenoid has self-inductance L. If its length is doubled, keeping total number of turns constant, then its new self-inductance will be, guys, see, we say self-inductance is equal to mu naught n square A into L. And what is this small n? Always remember, it is number of turns per unit length, total number of turns per unit length. We say it is total number of turns per unit length. It is like, guys, we say charge per unit length, that is total charge by total length. Charge per unit area, total charge by total area. Similarly, it is total number of turns divided by total length. So N is capital N divided by L. So you can write over here L. This is self-inductance and this is the length. Guys. So this will be N mu naught. Instead of N, you can write capital N square A into L divided by, this is L square over here. This and this will cancel. So L will come out to be mu naught N square A divided by L. Okay, this L is the length. It says that a long solenoid of self-inductance L, if its length is doubled, it says that this length is doubled. Okay, and clearly you can see this L is inversely proportional to L. If the total number of turns is constant, it says that this L is doubled. We say this self-inductance is halved. It becomes half, so L by 2. Option 1. So it depends, guys, it depends. If they say total number of turns is constant, we say then L is proportional to this L, inversely proportional to L. I'll tell you. I have actually put up a question over here. Guys, see, remember, I'll tell you over here. What is that? We say as self-inductance is mu naught n square A into L. Okay. We say if n is equal to constant, if number of turns per unit length is constant, then this L is directly proportional to length. Self-inductance is directly proportional to length. And we say this L, we also write it something like this, mu naught. Instead of small n, we can write capital N square divided by length into A into this length. Length is square. This square will cancel. So this will come out to be mu naught n square divided by L into A. Now, if total number of turns is constant, in such case, we say this self-inductance is inversely proportional to length. Now it depends upon the question. If they give you the total number of turns is constant, then you say self-inductance is inversely proportional to the length. If they give you the number of turns per unit length is constant, then self-inductance is directly proportional to the length. Guys, tell me in the chats if this is clear and crystal. Everyone means everyone. Guys, smash the like button if you have not liked the session yet. Great. Now, guys, let's take a look at this question. A long solenoid of 1000 turns, when a current of 4 ampere flows through it. It says that solenoid means this coil. We have got a coil of, we say, 1000 turns. When a current of 4 ampere flows through it, so 4 ampere current flows through it, the magnetic flux linked with each turn, in this case, it says that flux through each turn is phi is equal to 4 into 10 raised power minus 3 Weber. So in every single turn, how much is the flux? In each turn, how much is the flux? That is 4 into 10 raised power minus 3 Weber. AC will be in the next lecture. So we say flux in each turn will be 4 into 10 raised power minus 3 Weber. The self-inductance of this coil is, we are supposed to find the value of this. We are supposed to find the value of the self-inductance. Now guys, flux through each turn is this. And how many turns are there? 1000. Now can I say flux through 1000 turns? So that will be how much? That will be 1000 into flux through each turn. So flux through each turn will be how much? 4 into 10 raised power minus 3. and. So this is the total flux. This will be, we say, sir, phi total. So flux through 1 turn is this much, flux through 1000 turns is this much. And I can say, my dear friends, in this particular case, so also, we can say this flux will be L into I. Phi is equal to Li. Recently, we studied this. So flux will be how much? That is 1000 into 4 into 10 raised power minus 3 is equal to self-inductance. In this case, we are supposed to find out. Current is given as 4 ampere. 4 and 4 will cancel. 10 raised power 3, 10 raised power minus 3. L will come out to be 1 Henry. So 1 Henry is the correct answer. Okay. Is that clear? Is that clear, guys? Now, guys, let's take a look over here. Let's take a look at this question. See, the network shown in the figure. Okay. We are supposed to find the VA minus VB. This is a very good question. And it is very simple. I'll make you understand. I'll make you understand this question. It is very simple and it is very good. See. In this case, it is a question which is like the question of current electricity. I have shown you a lot of questions before in the current electricity chapter like this. What is the first thing if you want to find the potential difference between A point and B point? What is the first thing you guys are supposed to do? We say the first thing is select the path. Select the path. I'll tell you. So if you are selecting the path from A to B, let's suppose we are selecting the path from, we say, A to B. I'll mention over here, this will be from A to B. In order to solve this question, what is the first thing you guys are supposed to do? Select the path. So I'm selecting the path from A to B. Then we say, instead of all of this, I'll make the batteries over here. Guys, see, we say the direction of the current in this branch is something like this. So we know, sir, current always flow from higher potential to lower potential. So this will be positive terminal, this will be negative. If the direction of current was this, then I would have said this is positive, this is negative. Okay. Now guys, in this particular case, let's first find the potential drop in the resistance. Then we'll find the potential drop in case of the battery. Okay. See guys. I say in a resistor, let's find the potential drop, my dear friends. We say V is equal to I into R. Okay. So how much is the current? Current is flowing in this branch, that is I. I is given as how much? That is 4 ampere. That is 4 into. What is the value of resistance? That is 1. So it will be 4 volts. So if I replace this resistance with the battery, it will be having how much potential difference? That will be 4 volts. Let's talk about the inductor. In inductor, this is also called the inductor or the coil. Now, my dear friends, we say this V is equal to L di by dt. L di by dt. Now, in this case, L is given as inductance of this is given as 5 Henry. So I can say V is equal to, this is given as 5 millihenry. So 5 into 10 raised power minus 3. And di by dt, so current is increasing at a rate of 10 raised power 3 ampere per second. So this is given as 10 raised power 3. So this and this will cancel. So V will come out to be 5 volts. So in case of inductor, you got the potential difference as 5. In case of the resistance, so what is the first thing you guys are supposed to do? Select the path. Then find the potential difference in case of the resistance, and find the potential difference in case of the inductor. Okay. Now, my dear friends, we say replace all these with the batteries. Replace all these with the batteries. I would want you guys to replace all these with the batteries. So my dear friends, first I'll write over here VA, and then instead of this, I'll make a battery over here, which is having the how much potential difference? 4 volts. So this is positive, this is negative. So I'll say this will be positive, this is negative. And this is 4 volts. And then we have got a battery itself over here. Then we have got a battery over here, which is 12 volts. And here in this case, guys, tell me one thing. If this is the direction of the current, and it says that the current is increasing at a rate of this, don't you think that, sir, if the increasing current enters the inductor, it will create the induced current, which will oppose the primary current. This is the primary current, so this will be the direction of secondary current. If this is the direction of secondary current, we say this is only possible if you make the positive terminal from this side, negative from this side, because then only current will be towards left. Okay. And in this case, I can say, my dear friends, then we reach the point B over here, that is VB. Then we reach the point B, that is VB. Okay. So I can say this is VA. And how much is the potential difference in case of the inductor? We got as 5 volts. Now guys, tell me. Now find the potential difference. First we replaced all of these with the batteries. Now this is VA. Then we are moving from higher potential to lower potential. Guys, because this is our path. We are moving from higher to lower. So we take this potential drop as negative. And then here in this battery also, we are moving from higher to lower. So this will be minus 12 volts. Okay. And then we are moving from higher to lower. This will be minus 5 volts is equal to, finally we reached point B. Okay. So we say VA minus 21 volts is equal to, we say VB. Take it over here. VA minus VB will come out to be 21 volts. Guys, is this clear? Please give me the signal in the chats if this is the crystalline, if this is crystalline clear to each and every single student. Tell me, guys. Let's solve the similar type of question. Yeah, this one. Could you solve this? Guys, replace all of these with the batteries over here. Now, if this is the direction of the current, we say this will be the positive terminal. this will be the negative terminal. Current flows from higher to lower. Now, we'll replace this with the batteries. So this will be the battery in this case. And this will be the battery over here as it is. Now, instead of this, guys, here it says that current is increasing at a rate of 10 ampere per second. So if this primary current is increasing, don't you think that, sir, secondary current will oppose this primary current? Secondary current is in this direction. It is only possible if higher potential is from this side, lower is from this side, then only current will leave from this terminal. So this will be VB. This is VA. Now, I can say in this particular case, how to find the potential difference of this V is equal to I into R. Sir, current is how much? 4 ampere. R is 2. 4 into 2 is 8 volts. That's it. In case of resistance, we say I into R. In case of inductor, we say L di by dt. Okay. And what is L? L is given as 10 Henry over here. This is 10. And what is di by dt in this case? Di by dt is given as 10. So 10 into 10 is, we say, sir, 100 volts. So I'll say this will be 100 volts. And this over here is 5 volts. Okay. Now I am moving from A to B in this particular case. So I can say, if I'm moving from A to B, I can say this will be VA. Then if I'm selecting this path, then I can say minus, we say 8 volts. Then we say minus, we say 5 volts. Minus, we say 100 volts is equal to, we say VB over here. Okay. And over here, I can say VA. This is how much? Okay, 108, 113 minus VB will come out to be 113 volts. Let's solve the similar type of question on the same concept, this one. Okay, so I say in this case, find VA. Okay, find VA. And let me just give you in this case, L is given over here. Let me just give you over here di by dt in this case is di by dt in this case is minus 0.5 ampere per second. Ampere per second. What does this mean actually? What does this mean actually? This means the current is decreasing at the rate of 0.5 ampere per second. Current is decreasing at the rate of 0.5 ampere per second. Solve this. Guys, replace these with the batteries. With the batteries. So I'll write over here, this will be VA. And now you have got over here this battery, make it as it is. You have got this capacitor. This is the positive plate of the capacitor. This is the negative plate. So this will be higher potential. This will be lower potential. Now guys, this is the inductor. Understand this very carefully. This is the direction of the current. So we say if this is the direction of the primary current, this is the primary current over here. And this primary current is decreasing. We know this inductor will support the decreasing current. So direction of secondary current will be in the same direction. It is only possible if positive terminal is from this side, negative is from this side. In this case, we say, sir, this is the direction of current. So means this will be positive terminal, this will be negative, because current flows from higher potential to lower potential. So here in this case, this will be the lower potential. From this side, it is higher potential. And then you have got this over here, that is VB. And this point VB has got the potential 0 because it is grounded over here. Okay. Now guys, what is the EMF or potential difference of this battery? That is given as 5 volts. Now, let's write the potential difference in case of this capacitor. Tell me one thing. We say as in a capacitor, we say Q is equal to C into V. So V is equal to Q by C. What is Q over here? Q is given as 2 microcoulomb. C is given as 10 microfarad. 2 ones are 2 fives are. That is 1 by 5 volts. So instead of this, I'll write over here 1 by 5 volts. Then this inductor. I'll write in inductor. So can I say in case of an inductor, we say V is equal to L di by dt. Find the magnitude only, ignore the negative sign. So V is equal to, what is the value of L? L is given as 50. Di by dt is given as 0.5. So 0.5. So 0.5 is 5 by 10. Okay. So it is 50 into 5 by 10. 50 into 5 by 10. This and this will cancel. 5 into 5 is 25. So this will come out to be 25 volts. 25 volts. Okay. Then in case of the resistor, we say V is equal to I into R. So I can write over here V is equal to, what is the value of current? Value of current is given as 2 ampere. R is 4. 2 into 4 is 8 volts. So this will be 8 volts. Now guys, select the path. So first I'll write VA. Then we are moving from higher to lower. Okay. So this will be minus 5 volts. Higher to lower, minus 1 by 5 volts. Higher to lower, minus 25 volts. And here it is from lower to higher. Whenever we move from lower to higher, we take its potential drop as positive. 8 volts is equal to, we say, sir, this is 0. And solo this VA will come out to be 22.5 volts, 22.2 volts. Yeah, I took the minus 25 over here, na? I took minus 25 only. No, here you are saying, no, here you mention only magnitude. Forget about the sign here. Forget about the sign. Here you find the magnitude only. Okay, you don't have to focus on the signs over here. We'll take the break exactly at 11. Okay, till 11 we'll be finishing this topic. Now guys, let's take a look in this case. Magnetic energy stored in a solenoid or in an inductor. Okay, this means solenoid or we say inductor. Guys, let's suppose, my dear friends, you have got a coil or inductor, whatever you say, in which current I is flowing. Okay. What I'm trying to say is that, let's suppose previously you have studied, if you have got a capacitor, its potential difference across it is V. We say energy stored in the capacitor is 1 by 2 CV square. This we have studied previously. Energy stored in a capacitor is how much? CV square. Now, I have got a inductor over here and current I is flowing in this inductor. What is this current? This current is energy itself. This is power. This is charge. So we say whenever current goes in an inductor, energy is stored in it. Energy is stored in it. Whenever current goes in an inductor, energy is stored in it. And my dear friends, we say that energy will be 1 by 2, we say L I square. What is L? L is the self-inductance of this inductor. Like here we have 1 by 2 CV square. Here it is 1 by 2 Li square. And we know as this self-inductance is mu naught N square A into L, where A is the area of the cross section, L is the length of the inductor. So you can say this energy will be, that is 1 by 2. Instead of this L, you can write mu naught N square A into L. And then you will write over here this I square. You can write it something like this also. And my dear friends, I can say also if you divide this over here, so you'll say, sir, this is energy U divided by A into L will be simply, that is 1 by 2 mu naught N square into, we say, sir, I square. Now what is this energy divided by AL? So this is energy divided by volume, because if you find the volume of this cylinder over here, so that will be area of cross section multiplied by the length, area of cylinder. So this will be 1 by 2, that is mu naught N square into I square. So this is energy per unit volume. Or we say this is energy per unit volume, or we say this is energy density. This is energy per unit volume / you call it the energy density. So this is equal to 1 by 2 mu naught N square into I square. And what is this? This is the total energy stored in the inductor. It is like, let's suppose I am saying that you have got a cylinder over here. Sir, how much is the total energy in this entire, how much? Let's suppose you fill the water. How much is the total water stored? You say, sir, 4 liter. How much is the water present in the unit volume? That is the amount of water per unit volume. Similarly, how much is the energy stored in the entire volume? How much is the energy stored in the unit volume? That will be energy per unit volume is 1 by 2 mu naught N square into I square. Is this clear? Is this clear, guys? Is this clear? Please tell me in the chats. Is this clear? Please tell me in the chats. Okay. Now the topic is we have left, that is growth of current. Okay. So before this, I will take the break. Okay. So the break till we say 11:20. We'll get done with this mostly by 12 o'clock. Okay. Now guys, let's basically move on to the growth of current. Let's move on to the growth of current. Let's understand this concept, that is growth of current. Okay. Just a second. Let's understand the growth of current. Okay. Let's understand the growth of current. See guys, when it comes to the growth of current, I would want you guys to exactly focus over here. See, what does growth of current mean? Or we also call it the charging of inductor. Either you call it the growth of current or you call it the charging of inductor. It's one and the same thing. It's one and the same thing. Now guys, see, what is this growth of current? Let's suppose I am taking a circuit over here, and in this circuit you have an inductor, you have a resistor, and you have got a battery connected to this circuit, and then you have got a key over here. This is the key, switch. And right now the key is we say open. Key is not closed, the key is open exactly over here. We have not connected the circuit as of now. We have not connected the switch as of now. I would want you guys to basically answer me. When the key is not connected, could you please tell me how much is the current in the circuit? We say, sir, current is 0. Now let's suppose I'll connect this key. So when key is just closed, understand this very carefully. When key is just closed, what does that mean, guys? Now current wants to become maximum. I'm saying you have got a circuit over here. This is the 10 ohm resistor, and you have got a battery of, let's suppose, 100 volts. Okay, there is a key over here. Once you connect the key, we say, sir, current flows in the circuit. It becomes V divided by R. V is 100, R is given as 10. So it will become, sir, 10 ampere immediately. So we say when key is just closed, we say current in at that point is 0. It is just we are about to close the key. We're about to close. When it is closed, no doubt then the current will start growing, increasing. But at the time of closing, we say current is 0. Okay. But current wants to change. Current wants to change. I would want you to focus over here. We say, but current wants to change. So I say di divided by dt is not equal to 0. Guys, I'm saying when you close the key over here, okay, when you close the key over here, when it is just closed, at that point of time current is 0. Now current will start growing, but di by dt is not 0. Current wants to change. Right now current has the maximum here the circuit has the maximum capability that it wants that current should actually change. Current has the maximum capability to change right now. Okay. Now guys, what if I tell you in this particular case, potential difference across this inductor is VL, potential difference across this resistor is VR. So this is the potential difference of the battery, which is divided into inductor and resistor. Okay, so at this point of time, could you please tell me what is the what is the potential difference? Guys, I would want you to focus. What is the potential difference in case of the resistor? We say as in resistor, we say V is equal to I into R. So if the value of current is 0, so we say 0 into R will be 0. So initially, this VR, potential difference across the resistor, is 0 and we call this as initial state. Initial state. Initial state means when key is just closed. When key is just closed. Now tell me guys. And when it comes to in case of inductor, I'll write in case of an inductor. In case of an inductor, I'm saying, sir, this VL is equal to, that is L. Then we say DI divided by DT. This is how we find the potential difference in case of an inductor. If guys, DI by DT initially is maximum, current wants to change. So I can say VL will be maximum. VL will be maximum. Okay. VL will be maximum. Okay. So initially I can say in this particular case, my dear friends, potential difference. So we say EMF of the battery, You can say, sir, this EMF of the battery is divided into, we say, potential difference across the inductor plus potential difference across the resistor. And here, initially, we say VR is 0. So initially, VL is equal to, E is equal to VL. So all the EMF of the battery is we say go into the inductor. So this is, we say, initial state. This is what we call the initial state. And then we say finally, or final state. And when it comes to the initial state, we say at t is equal to 0. T is equal to 0 means that is initial state when current is equal to 0. And final state, or we also call it the steady state. Okay. So means when t is equal to infinity. In case of final state, steady state, we consider, now you have closed the switch. Okay. You have closed the switch. We say now I can say in this particular case, the current has become the maximum. That is, we say, sir, I naught, and it is now constant. Guys, right now, initially, wait. I am saying when key is just closed, at that point of time, current is 0. Now current increases, reaches the maximum value. And that maximum value, when the current reaches, is what we call the final state. At that point of time, we say time is equal to infinity. And right now, we say di by dt, change in current, will be 0. Why? Because the current has already become maximum. When any quantity is maximum or constant, we say its change will be 0. So that's why di by dt will be 0. Now, can you tell me, finally, in this circuit, what will be the value of, sir, VR, potential difference across a resistor? You say, sir, that will be I into R. If current finally is maximum, so this will be maximum, VR will be maximum. And when it comes to the VL, we say this is L di divided by dt. We say L di divided by dt. Now, my dear friends, in this particular case, if I say, sir, di by dt finally is maximum, so we say, sorry, 0, we say VL will be finally 0. And finally, potential difference of the battery is getting completely into the potential difference across the resistor. Is this clear? Please tell me in the chats. Okay. So we say this is the initial state, this is the final state. Now guys, if I say in between the two states, between the two states, current is growing. Current is growing. My dear friends, you say at time t is equal to 0, current is 0. You say at time t is equal to infinity, current is maximum. So means, let's suppose initially current is 0, maximum value of current is 10 ampere. So means current has grown 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So from this t is equal to 0 to t is equal to infinity, we say current has grown over here. We say current has grown over here. Current has grown over here. Okay. So my dear friends, I would want you guys to focus exactly over here. I would want you to focus. We say, in this case, in between the two states, current is growing. We say it is due to the inductor. It is due to the inductor. It is due to the inductor. We say as inductor opposes the change. Inductor opposes the change. So my dear friends, let's suppose if it was only resistor present in the circuit over here. Okay, we say, sir, this is 10 ohm resistor. This is 100 volt battery. Now, when you close the switch, you say, sir, current will become 10 ampere immediately, because only resistor is present in the circuit. But when it comes to the inductor, we know when you close the switch, now current wants to change, wants to become the maximum. So when you send the increasing current through this inductor, we know inductor opposes the change. Inductor will never want that current should increase through it. So it will oppose that change. It will oppose that change. So it does not want the current to become maximum immediately. Current will be maximum, but after some time. So we say growth of current will take place. That's why we say it is due to the inductor which opposes the change. We say growth of current takes place. We say growth of current takes place. Guys, if there was no resistor, there was no inductor present in the circuit, I say growth of current would not have taken place. It would have gone directly from 0 to maximum immediately. But because of the resistor, we say it will take time to become maximum. Okay. So we say it. So current takes time to become maximum due to the inductor. And my dear friends, in between the two states, so here current is growing according to this equation. Your current is growing according to this equation. And what is that? Guys, see. I say I is equal to, we say I naught 1 minus e raised power minus RT by L. I is equal to I naught e raised power minus RT by L. You say, sir, from 0 to maximum current is increasing. I completely understand. Is current increasing according to this relation? I is equal to T square, means when time is 1, current is 1. When time is 2, current is 4. When time is 3, current is 9. I say no, not according to this relation. Current is increasing, current is growing according to this equation. This is how current is growing in the circuit. So I hope you got it. See. Growth of current takes place because of the inductor. Because inductor opposes the change. Inductor does not want the current should be maximum immediately. Okay, current will be maximum, but after some time it will grow. That's why we call it the growth of current. If there was no inductor present in the circuit, it would have gone maximum immediately. So according to this relation, this is what we call the growth of current. According to this relation, current grows in the circuit. Current increases in the circuit. Guys, tell me in the chats, is this clear till over here? Guys, tell me in the chats if this is clear till over here. Everyone. Okay. Now guys, one more thing I would like to tell you over here. What is that? That is time constant tau. Time constant tau. Guys, we say this time constant tau is equal to L by R. We say this time constant tau is equal to L by R. Okay. What is this? And guys, see. What is I naught? I naught is the peak current. We say I naught is the maximum current. Okay. What is R? R is the resistance of the resistor. T is the time. L is the inductance of the inductor. Now guys, in this particular case, what I'm saying is that time constant is L by R. Now can I say 1 upon this tau is equal to, we say R by L. Okay. Now in this particular case, we say put in the equation 1. I would want you guys to put this in the equation 1. So I can write over here I is equal to, we say I naught 1 minus e raised power, and over here it is minus RT by L. Instead of R by L, I'll write over here 1 by tau. So it will become T by tau. Now, this came out to be the equation. Now, let's suppose at time T is equal to tau. Let's suppose I'm saying the value of time is exactly the whatever is the value of tau. If I say both have got the same value, if I say value of tau is 10, let's suppose we say time is also 10. So what will be the value of current? So current will come out to be, sir, I naught 1 minus e raised power minus 1, because both will cancel. It will be e raised power minus 1. So I can say this I will be equal to I naught 1 minus 1 divided by e. What is this 1 by e? Value of 1, because see, e raised power minus 1, if you take in the denominator, it will be 1 by e. 1 by e is 0.37. We can say I will be equals to, that is I naught 1 minus 0.37. I naught 1 minus 0.37. Okay. So 1 minus 0.37 is how much? We say, sir, it will be I naught into 0.63. What does this mean? So this is the current when time is equal to tau, when time is the time constant tau. So means. Can I define over here? Time constant is that time at which current has reached the 63% of its maximum value. At which the current has reached 63% of the maximum value. If I say, sir, after t is equal to 5 seconds, how much is the current? Sir, current has reached 50% of its maximum value after t is equal to 10 seconds. Similarly, sir, at time constant tau, we say current has reached 63% of its maximum value. So let me summarize this, guys. What I'm trying to say in this case, we say you have got a circuit over here in which inductor is used. When you close this circuit, when you close the switch, we say current will flow and it wants to become maximum immediately. But inductor is present in the circuit, it will not let the current to become maximum immediately, so it will oppose the change. It will oppose its increasing nature. Now current will increase, but it will take some time, so that is what we call the growth of current. So I can say here, in starting inductor opposes the current, and in starting we say it behaves like an open wire because it is opposing maximum. It is opposing maximum. Guys, tell me in the chats if this is clear, crystal to each and everyone. No, it is not necessary. If I am saying if we use inductor in this circuit, then what happens? Then growth of current takes place. Okay. This is a concept. If you are using the current in the circuit, then growth of current takes place. Sir, if I do not use, then no growth will be there. Then current will reach the maximum value immediately. No. Final state is when t is infinity, when current is maximum. Key is still closed. When current is maximum. Okay. So we say, so remember from now onwards, we say at t is equal to 0, inductor behaves like an open wire. Inductor behaves like an open wire because at t is equal to 0, the opposition by inductor is maximum to the increasing current. The opposition to the increasing current by the inductor is maximum. So we say inductor behaves like an open wire. Now guys, let's take a look at this question. Compare the brightness of a bulb at t is equal to 0 and t is equal to infinity. You guys are supposed to compare the brightness of the bulb at t is equal to 0 and t is equal to infinity. Very important question. See guys, you have got this bulb, you have got this resistance, you have got this bulb B2, this inductor over here. When we talk about t is equal to 0, can I say t is equal to 0 means when switch is just closed? T is equal to 0 means when switch is just closed. And guys, when switch is just closed, I say inductor behaves like an open wire. Inductor behaves like an open wire. Okay. And at t is equal to 0, I recently told you, potential difference across resistance is 0 and potential difference across inductor is maximum. You can clearly see over here. At t is equal to 0, VR is equal to 0 and VL is equal to maximum. Now guys, take a look over here. In this case, we say this battery is connected to this branch BD. It is connected to this branch AC in parallel. This branch and this branch is parallel. If I say 10 volt potential difference is across this branch, 10 volt potential difference will be across AC branch also. Now, in this particular branch at t is equal to 0, we say this bulb, either you call it the bulb or you call it the resistance. Either you call it the bulb or you call it the resistance. Just a second. Hello. Generate ka daba. Huh? It's another. Okay. Now, guys, we say VR in this case is 0, VL in this case is maximum. So either if this is a bulb, you can consider this bulb as a resistance also. Bulb is a resistance. So we say at t is equal to 0, there is no potential drop across this resistance. So we say, guys, there is one more formula. Power is equal to V square divided by R. So we say power across this bulb is 0 in starting. Why? Because voltage across this bulb is 0, so power across this bulb is 0. So we say initially, so B2 will not glow, okay? Because initially at time t is equal to 0, all the potential difference given by the battery will be given to the inductor. Now guys, let's talk about this. Sir, this battery, let's suppose it is sending 10 volts of potential difference. 10 volt will be given to this branch also, this branch also. In this branch, there is no inductor present. It is only resistance, it is only bulb. So this potential difference will be divided between this resistance and this resistance. Okay, let's suppose 5573, depends. Okay, so we can say and in which branch is this? We say, sir, BD branch. We say B1 will glow. B1 will glow. Sir, this B2 will not glow because this potential difference is completely taken by this. This potential difference is completely taken by this inductor over here. Okay. It is completely taken by the inductor over here. Now guys, in this particular case, we say B1 will glow. So I can say brightness of B1 is greater than brightness of B2 at t is equal to 0. But when it comes to infinity, at t is equal to infinity, I say at t is equal to infinity. At t is equal to infinity. Okay. At t is equal to infinity. Now guys, so we say at t is equal to infinity. At t is equal to infinity. at t is equal to infinity. Okay. At t is equal to infinity. I can say potential difference and at t is equal to infinity, we say potential difference across inductor will be 0 because we have discussed this, and potential difference across resistance will be maximum. I recently told you at t is equal to infinity, potential difference across resistance is maximum, across inductance it will be 0. So I can say over here, finally, sir, across this potential difference will be 0 and it will behave like a simple wire and all the potential difference will go over here. So we can say power across the bulb will be maximum. Why? We say power is V square by R. If V is maximum, we say power will be maximum. Okay, so I can say, sir, finally, this B2 is greater than, we say, sir, B1. Finally, B2 is greater than B1. Sir, finally, at t is equal to infinity, what about this? About this, we say, sir, the potential difference will be divided between this and this. But when it comes to initially, here, potential difference across this will be 0. Finally, potential difference across this will be maximum. Sir, finally, will this bulb glow? Yes, this will glow initially as well as finally, but with less brightness. Finally, this will have more brightness. More brightness. Okay. 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 Is this clear, guys? Please tell me in the chats. Guys, is this clear? This is a proper conceptual question. This was just an example. Now, guys, let's suppose we have this question. Find the current passing through the battery at t is equal to 6 seconds. Guys, see, we say from the battery current I is coming out. Okay. From the battery current I is coming out. And from the battery current I is coming out. And I can say in this particular case, this current is going inside this and the current is going inside this. So this will be current in the inductor and this will be current in the resistor. You have to tell me what is the value of this net current. Guys, see, in this case, we say this battery is connected to the inductor, the battery is connected to the resistor also in parallel. Let's find the current in the resistor. So I is equal to, we say IR is equal to, current in the resistor is equal to V divided by R. Because we say V is equal to IR, I is equal to V by R. And what is the value of potential difference? That is 20 volts. What is the value of the resistance over here? That is 10. So this will be exactly, that is 2 ampere. 2 ampere is the value of current in the resistance. Now, how do you find the value of current in the inductor? Now, guys, see, current in inductor. Now, current in inductor. Guys, see, in this particular case, I'm saying, if you have to find the current in the inductor, let me show you. how we are supposed to find the current in the inductor. As we say, as V is equal to L di by dt. This is how we find the potential difference in case of the inductor. Now take this dt over here, so it will become V dt is equal to L di. Now I would want you guys to integrate. Now integrate. So this potential difference is constant, take it out, so it will be integration of di is equal. Take this L out, integration of it will be di. Now guys, here this and this will cancel, this and this will cancel. So I can say it will come out to be V into I will be equals to, we say this is V dt, this is V dt. So we say V into T, we say V into T will be equal to L into I. So I will come out to be, that is V divided by L into T. V divided by L into T. Now my dear friends, if you want to find over here this current, we say sir. Now in this case, if we have to find the current, sir, potential difference across this inductor is given as 20 volts divided by inductance of this is given as 3. At time it is asking, sir, 6 seconds. So this is 6, 3 ones are 3, 2s are 2 into 20 is, sir, we say, sir, current in the inductor is 40 ampere. Now, current in the resistor is 2 ampere. This is 40. So total current will be simply current in the inductor plus we say current in the resistor. So this will be, that is 42 ampere. This will be 42 ampere. Okay, let's talk about this one. The ratio of initial to the final current through the battery when switch is just closed. Guys, ratio of initial to the final. We say initially at t is equal to 0. T is equal to 0 means initial state. Initial state means when switch is just closed. Okay. Guys, when switch is just closed, could you please tell me one thing? Sir, what about the inductor? Inductor is present over here. We say inductor behaves like an open wire. We say at t is equal to 0, inductor behaves like an open wire. Okay. So if I make this circuit, I'll make it something like this. This is the resistance at the top. And here it is the open wire. And then you have got this resistance. You have got this battery, this resistance over here. Okay. So this is R, this is R, this is R, and this is, we say, sir, E. And in this particular case, my dear friends, listen to me very carefully. In this particular case, my dear friends, I can say over here. See, I can say in this particular case, we say, sir, current will not flow in this branch. Why? Because it's an open circuit over here. Could you please tell me how much will be the current? We say current will be V divided by R equivalent. And R equivalent is how much? This R plus R, that will be 2R. So I will be simply V divided by 2R. And instead of this V, I'll write E over here, E by 2R. And when we talk about finally, we say finally, at t is equal to infinity, we say inductor behaves like a simple wire. Okay. So finally, inductor behaves like a simple wire. So if I make the same circuit, finally, this resistance, battery, this resistance, R. Now, how much is the current finally? Guys, what is the R equivalent in this case? This R and this R is in the series. Sorry, parallel. So this will be R by 2. Their equivalent is R by 2. And that is series in this R with this R. So R equivalent in this case will be simply R by 2. That is equivalent of these two. With this, it is in series plus R. So it will be 3R by 2. 3R by 2. Now let's find the current. So current finally will be, that is V by R. V is E and R equivalent is 3R by 2 and 2 I'll take over here. Now in this particular case, I can say this is current initial. So I initial divided by I final. It will come out to be, that is E by 2R upon, we say 2E divided by 3R. Okay. Now take it in the numerator. It will be something like this, E by 2R multiplied by, so this is 3R. Okay. E by 2R upon 3R divided by 2E. R will cancel, E will cancel. So 2 into 2 is 4. So it is 3 by 4. So ratio of initial current by final current is 3 by 4. Is that clear? Is that clear, guys? Tell me. Yes, current is not flowing means current is 0. Let's talk about this one. Guys, in this particular case, if you take a look over here, figure shows a circuit contains 3 identical resistors with resistance R is equal to 9 ohms and inductor 2 millihenry. EMF is this. Find the current when the switch is just closed. It says that when the switch is just closed, we know that inductor behaves like an open wire. So let me redraw this figure. It will look something like this. This is a battery over here. And then here, this, it becomes open wire. Why? Because inductor is present in this. So it becomes open wire. So I'll not make it. I'll not make it. There is no need to make this. Why? Because current does not flow in the open wire. And this resistor you will have to make. Here also it is open wire. Here also it is open wire. So only this resistance and this battery, this is E, and this will be the resistance, this is E. Now, how much will be the current in this case? That is E divided by R. What is the value of E? E in this case is given as 18 volts. Resistance is given as 9 ohms. So that is 2 ampere. So 2 ampere is the correct. This is a previous year question. This is a previous year question. Okay. The same here also. The current through the battery just after the switch is closed. We say here it is an open wire. Here it is an open wire. Okay. And when it comes to the capacitor, we say it behaves like a simple wire. Simple wire. At t is equal to 0, capacitor behaves like a simple wire. At t is equal to infinity, capacitor behaves like a open wire. Just remember it directly. Now I can say in this particular case, guys, we say this resistor is gone. And here, you have got one resistor, another. Let me make this circuit. You have got the battery over here, this resistor and this resistor. This will be R, this will be R, and this is E. If you have to find the equivalent resistance, for these two, equivalent resistance will be R by 2 because they are in parallel. So current in this case will be V divided by R equivalent. So current is, what is V? That is E. R equivalent is R by 2. So current is 2E divided by R. And E is given as 18 volts. and R is given as 9. So we say 2 into 18 divided by 9. Okay, 9 ones are, 9 twos are. So I is equal to 4 ampere. So I will come out to be 4 ampere. Is this clear? Now, let's talk about this question, guys. Find the rate of change of current across the inductor. This is actually a very good question. This is actually a very good question. See, guys, you guys are supposed to find out the rate of change of current across the inductor. Means you have to find the value of di by dt at t is equal to 0, at t is equal to infinity. You don't have to find the value of current, but you have to find the value of the di by dt, change in current. See, guys, let's first do one thing. We say at t is equal to 0. Okay, let's suppose we say at t is equal to 0. When switch is just closed, we say when switch is just closed. Guys, always remember at t is equal to 0, current will be only 0 in that branch only where inductor is present, because over there it will behave like an open wire. Don't say in every branch. No, not in every branch. Only in that branch where inductor is present. Now, guys, see, I say at t is equal to 0, we say the circuit will look something like this. I'll make this circuit over here. So the circuit will look something like this. This is the resistance, this resistance, this resistance, and here it will behave like an open wire. Here it will behave like an open wire. So this is R, this is R, this is R, and this is E. It will behave like an open wire. Now, my dear friends, I can say over here, sir, what is the value of the current? Sir, no current flows in this branch. So only you have got these two resistors in series. So current will be simply V by R, V divided by, we say 2R. Because this resistance and this resistance is in series, V divided by 2R. Okay. Now, guys, let's suppose I am saying over here, what I'm saying in this particular case, is this is, let's suppose, VA, and let's suppose this is VB. Potential difference across the ends of the inductor. Here current is not flowing, so we have to find, we say potential, we have to find di by dt. Now, guys, tell me one thing. We say as potential difference is L di divided by dt. Take this L over here. So this will be V divided by L. This will be equal to d by dt. Now, guys, if somehow we get the value of potential difference across the inductor, so that is this means this. We'll divide it with the inductance. We can easily get the value of di by dt. So I am saying if this is the one end over here, this is A, this is another end, this is B. Potential of this end is VA, potential of this end is VB. So that is the potential difference across the inductor. That is VA minus VB. That is this V. If you find this, you'll get the answer. Now, guys, we say you got the current in the circuit. Now, this current is something like this. So it will flow. Here current will not go. Why? Because it's an open wire. So this current goes something like this. Means this is the positive terminal. This is the negative terminal. Current always flow from higher potential to the lower potential. Now guys, we say move in this loop. Now move in the loop to find VA minus VB, that is potential difference across the inductor. First, I'll write over here VA. First, I'll write over here VA. If I'm starting from point A, then sir, I'll have to write the potential difference of this, because this is how we write. If you have to move in a loop, I have told you this in the current electricity. So we say in case of this resistance, there is no current. So here potential difference is I into R. I is 0. So potential difference will be 0. I into R. 0 into R is 0. Now in this case, we say potential difference will be I into R. V is equal to I into R. And my dear friends, we are moving from higher to lower because this is our path. So we take this drop as negative. And then finally we reach point B. So is equal to, we say VB. Now in this case, I can write this VA minus this VB will be equals to I into R. Will be equals to I into R. Okay. Now I can say VA minus, we say sir, VB is equal to, let this current be as it is. Okay. Now what is the value of current that we have already calculated? That is, this is V by R. So you can write E divided by R because this battery is E divided by 2R. So this will be, this is E divided by 2R into, we say sir, this R. Now this R and this R will be cancelled. So it will come out to be E divided by 2. It will come out to be E divided by 2. Now guys, in this particular case, this is VA minus VB. So this is the equation first. We say put in equation first. If you put in the equation first, instead of this V, you will write E divided by 2L will be equal to di by dt. So this is what we were supposed to calculate. And we say at t is equal to infinity. At t is equal to infinity, we say di by dt is 0. Change in current across the inductor is 0 because current is constant. Guys, tell me in the chats how many of you understood this. Please tell me in the chats. Whosoever is watching, everyone means everyone.
Hello, if you're preparing for JEE 20.
Let's talk about the decay of current. Let's talk about the decay of current. Let's talk about the decay of current. What does the decay of current actually mean? Listen to me very carefully. Guys, we have got a circuit over here. I hope the circuit is visible. Okay. In this circuit, you have got an inductor. You have got an inductor. You have got a resistor R1. You have the battery over here. You have got one more resistor in this particular case. Okay. This is 1, this is 2, and this is 3. Guys, we say, in case of ingrowth of current, ingrowth, we have studied, we say ingrowth, if, like I'll write over here, in growth of current, if we join 1 and 3, we say this will be the circuit over here. We say if we join 1 and 3, then growth of current takes place. Growth of current takes place. Okay. And my dear friends, the circuit would be something like this. Guys, if you join 1 and 3, we say this lower part will not be included in the circuit. Why? Because this will be open. No current flows in the open branch. So in that case, this would be the circuit. This is the resistance. This is the inductance, resistance, and you have got a battery. This would be the circuit. And we have studied in this case, initially current is 0. Initially current is 0. Okay. Then finally current becomes maximum. Current becomes maximum. In between these two, growth of current takes place. Now guys, let's suppose if we join 1 and 2, understand very carefully, means we have disconnected the battery. Because of the battery, current was there. Now if you disconnect the battery, don't you think that now we say current wants to decrease? Current wants to decrease, it wants to become 0. We say if we disconnect the battery. Now guys, in this particular case, this would be, and here I can say in this particular case, this will be the resistor. So this will be the inductor over here. This will be the resistor over here. So this will be the circuit. So in the middle branch, current will not flow. Can I say here in this case, we say at t is equal to 0, we say what is the value of current? Current is already maximum. That has gone maximum because of the growth. And we say at t is equal to infinity, current will become 0. Because if you disconnect the battery over here, we say current will now start decreasing. And because of the inductor, we say current wants to become 0 immediately. But inductor is present in the circuit. It will not let that happen. Current will become 0, but it will take time. It will take time. We say current will try to become 0 immediately. But due to inductor, it will take time. It will take time. So when it takes time means current starts decreasing. So growth of current will take place. So I'll write, so growth, decay of current. Decay of current takes place. We say decay of current takes place. Okay, decrease in current takes place, decay of current takes place. And my dear friends, in this particular case, we say decay of current takes place. Decay of current takes place. And current will decrease according to this relation. Current will decrease according to this relation. We say I is equal to I naught e raised power minus RT by L. In case of growth of current, we say current increases, I is equal to I naught 1 minus e raised power minus RT by L. Okay, that will be the growth of current. And this is the decay of current. Now guys, in this particular case, I can say, if I define the time constant, we say time constant tau is simply that is L by R. And if you do the reciprocal, so 1 upon tau will be simply that is R by L. 1 upon this will be simply that is R by L. Now I would want you guys to put up over here. So current in this case will be simply I naught e raised power minus R T by L. Instead of this R by L, I would want you guys to put up the tau over here. So that will be T divided by tau over here. Okay. Now if I say at time T is equal to tau, we say current will be that is I naught e raised power minus 1. I naught e raised power minus 1. I naught e raised power minus 1. So I can say this current will be simply I naught into 1 by E. So what is 1 by E? The value of 1 by E is 0.37. So current in this case will be I naught into 0.37. So means time constant is that time also at which the current reaches 37% of its maximum value. Okay. So we say time constant is that time at which the current reaches 37% of its maximum value. 37% of its maximum. Okay. So this is how we define the time constant. And in this case, current is decreased according to this relation. Current decays according to this relation. Guys, if there was no inductor present in the circuit, then the current would have become zero instantly, immediately. But because of the inductor present in the circuit, it will not let that happen. So we say current will decrease, current will decay in this particular case. Okay. Now there is a concept, and then one more thing I forgot to tell you, that is over here in growth of current. Guys, let's talk about the graphs also. We say when it comes to the growth of current, if I ask you to plot the graph between, this is I versus T, current versus time. If I ask you to plot the graph between di by dt versus time, if I ask you to plot the graph between, we say VR versus time. If I ask you to plot the graph between VL versus time, guys, tell me one thing. We say at t is equal to 0, current is 0. T is equal to, we say, infinity, current is maximum and constant. So the graph will be something like this. At t is equal to 0, current is 0. After at t is equal to infinity, we say current will be maximum. This will be maximum and it is I naught. And when it comes to t is equal to 0, we say di by dt will be maximum. If you remember, in case of growth, okay, at t is equal to infinity, we say di by dt is equal to 0. So the graph would be something like this. At t is equal to 0, di by dt will be, at t is equal to infinity, di by dt will be 0. Similarly, VR versus time, we say at t is equal to 0. I told you, sir, potential difference across resistance is 0. At t is equal to 0, at t is equal to infinity, VR will be equal to maximum. So the graph would be something like this. And in case of inductor, it would be something like, okay. It would be something like this, because at t is equal to 0, potential difference across the inductor is maximum. That's why the graph starts from maximum. At t is equal to infinity, potential difference across inductor is 0. It is 0. I hope this is clear. I hope this is clear, guys. Okay. Let's talk about the mutual inductance. Guys, tell me in the chats if this is crystalline clear. Everyone out there, tell me. Okay. Now see, guys, let's suppose current in the first coil is flowing. Okay. Because of this current, if you remember in the magnetism, I taught you one concept. If the current is flowing in the coil, it produces the magnetic field at x distance. We say due to the current in coil 1, magnetic field is produced at x distance. Due to the current in coil 1, magnetic field is produced at x distance. Okay. Because of this current, we know if there is a current flowing in the coil, it produces the magnetic field on its axis. I have told you previously, B is equal to mu naught I into R square upon 2 into R square plus X square whole raised power 3 by 2. So magnetic field is present exactly at this point. Now this magnetic field is crossing the coil 2, which crosses the coil 2. If magnetic field crosses the coil 2, so flux is created. So can I say from this, sir, flux is directly proportional to the current. Flux in the coil 2 is proportional to the current in the coil 1. If more current flows in this coil, it produces more magnetic field at x distance. So more magnetic field will cross the coil 2, so more flux will be produced. Now replace the proportionality with a constant. Replace the proportionality with a constant. And I can say, my dear friends, that will be phi 2 will be equal to m into I1, where m is called mutual inductance. Why do we call it the mutual inductance? Because here current in the coil 1 is flowing and flux is created in the another coil. That's why we call it the mutual inductance over here. Okay. That's why we call it the mutual inductance. And when it comes to the value of this mutual inductance, we say this mutual inductance is simply equal to, that is mu naught pi r1 square r2 square upon we say 2 times of x cube, 2 times of. And my dear friends, what is this r1? R1 is the radius of first coil. What is this r2? R2 is the radius of second coil. What is this x? X is the distance between the two coils. This is the formula for mutual inductance. Now guys, if I say if the current in the first coil is changing. Then flux through coil 2 will change. Then flux through the coil 2 will change. And how do you write that change in current? So that is change in current in the coil 1 is di1 by dt into m. M is constant, is equal to flux in the second coil will change, that is d phi 2 divided by dt. Now what is this? Rate of change of magnetic flux with respect to time. So this is EMF. So we say this EMF is equal to minus m di1 by dt. So this is the EMF produced in the second coil. So this is the EMF induced in the second coil due to the coil 1 and the process is called mutual induction. So if you remember the previous case, self-induction, in the same coil current was flowing, in the same coil EMF was induced, but here EMF is induced in one coil and current is flowing in the another coil. That's why we call it the mutual induction. Okay. With the decrease in the primary coil, with the decrease of current in the primary coil is how much? So it says that with the decrease of the current in the primary coil from 2 ampere to 0 value, change in current in this case is given as 2 amperes. Okay. In 0.01 seconds, the EMF generated. Okay. Guys, in this case, it says that we have to find the mutual inductance. The EMF is given as, we can say, m di by dt. It says that in a coil, current changes from 2 ampere to 0 value. So how much is the change in current? 2 minus 0 is 2. So di in this case is given as 2. In 0.01 seconds, dt is given as 0.01. And EMF is 1000 volts. This is given as 1000 is equal to m. di is given as 2. This is 0.01. Okay. Now guys, in this case, you can write this is 1000 is equal to m into 2. You can write this as 1 divided by 100. So this will be 1000 is equal to m. 2 into 100 will be 200. This. So 10 by, so m will come out to be, that is 500. So mutual inductance in this case is 500. And we have the last topic of the session, and I'll get done with this in the next 10 minutes and we are done with the session. This is the last topic of the session. Okay. Induced electric field. Okay, this is the last topic of this session. Now guys, take a look exactly over here. Let's suppose I say I have got a ring over here. This is the ring that I have exactly over here. And in this particular case, I have a magnet. This is a magnet. And I'm taking this magnet close to the ring. Okay, I'm taking this magnet close to the ring. You know that magnetic field lines come out of this magnet. Magnetic field lines come out of this magnet. And these magnetic field lines are crossing this ring. These magnetic field lines are crossing this ring. The magnetic field lines are crossing this ring. Okay. Okay. Now guys, if these magnetic field lines are crossing the ring over here, tell me one thing. We say, as due to the change in flux through the coil, as due to the change in flux through the coil, we say EMF is induced in the coil. EMF is induced in the coil. Okay. And current flows in the coil. So current is induced in the coil or EMF is induced in the coil, it's one and the same thing. So if you are basically saying, taking the magnet close to the coil, I'm saying, sir, this is the current which is flowing in the coil. This is the current which is flowing in the coil. Now tell me one thing. If current flows in the coil, that means charge is flowing in the coil. So that is, charge is flowing in the coil. Because flow of current itself means the flow of charge. So we say this will be the direction of positive charge. Okay, this is the direction of positive charge. So same is the direction of positive charge. Okay, yes. And direction of negative charge is opposite. Okay. Now guys, tell me one thing. We say charge flows because of the electric field, because we have studied whenever you place the charge in the external electric field, we say force acts on it, it flows. So as charge flows due to electric field, so electric field is produced here. Electric field is also produced over here. So if this is the direction of the positive charge, same will be the direction of electric field. So I can say in this particular case, so we can say by changing the magnetic flux through the coil, electric field is being produced. By changing the flux through the coil, electric field is induced, known as induced electric field. Okay, so that is known as induced electric field. Okay, induced electric field. So what is induced electric field? If you take a magnet close to the coil, away from the coil, we say magnetic field through the flux through the coil will change. So flux through the coil will change. Current is induced. Current is induced means charge is flowing. Charge flows because of the electric field. So electric field. And we say, how do we write this electric field over here? We say, sir, this electric field, we write it something like this. Closed line integral EDL, closed line integral EDL is equal to, we say minus d phi divided by dt. What is that? Because of the change in flux through the coil, electric field is being induced. Sir, why did you mention this closed line integral? Because this electric field is sort of a cyclic loop over here. It forms a cyclic loop over here, closed loop over here. That's why I made it something like this. Closed line integral EDL is equal to minus d phi by dt, is equal to minus d phi by dt. This is the, we say, electric field which is being induced over here. Okay. Is this clear? So previously we were saying, sir, this is EMF is equal to minus d phi by dt. Even you can understand it something like this also. We say as we say EMF is equal to minus d phi by dt. What is this EMF? EMF is potential difference. We say also we know V is equal to minus E is equal to minus dV by dx. This is the relation between electric field and potential difference. Now take it over here. So this dV will be minus E dx. Now my dear friends, do the integration. So this will be delta V is equal to minus integration E dx. And here you can either write it delta V, or you can also write it the EMF is equal to minus integration E dx. Okay. Now here this EMF, this. So you can replace it with this one. So you can say closed line integral E dx is equal to d phi divided by dt. So same, that is what I was explaining over here. It's one and the same thing. Now we have a question in this case, that is induced electric field inside the region of magnetic field. Induced electric field inside the region of magnetic field. What I'm trying to say is that we have got a magnetic field over here. Okay, this is the magnetic field. Okay, and let me make it something like this. Let's suppose magnetic field is present in this region. This is the magnetic field which is present in this region. Okay, magnetic field is present in this region. And this magnetic field is changing. You have to find the electric field inside the region of magnetic field. Induced electric field inside the region of magnetic field. Now guys, you take a circular coil over here. And we say this magnetic field is present in our region. You have to find the electric field at our distance. Guys, sir, is this a ring? No. This is the region of magnetic field. A region of magnetic field, changing magnetic field. And this magnetic field is present in which region? Capital R region. You have to find the electric field at small r region, at small r distance, on this ring. I'm saying that in this case, we say, let's suppose magnetic field here will be, sir, E. And let's take a small, because at r distance magnetic field will be E. At this r, E. Let's take a small element over here of this ring as dl. Can I say in this particular case, as we know, we recently studied closed line integral. We say EDL will be equals to, we say we say minus d phi divided by dt. So this is how we find the electric field. Guys, magnetic field is present in the capital R region. You have to find the electric field at small r distance. So I say take the electric field out over here. So it will be closed line integral dl is equal to minus d by dt of. What is this flux? Flux is basically magnetic field into area, B into A. Now what is this dl? So dl means if you integrate all of these small dl's, you'll be getting the area of, you'll be getting the circumference of this ring, that is 2 pi r. So that will be 2 pi into small r is equal to minus d by dt of magnetic field. Area, sir, area of what area you guys are supposed to take in this particular case? Guys, see. In this particular case, you have to take, guys, what is this d phi by dt? This is change in flux with respect to time. So you have to take the change in flux. How much flux is changing through this coil only? Do not say I'll take pi into capital R square. No. The magnetic field is present in the capital R region. There is no doubt in that. But you have to take only that much of flux change in flux, which is present in this small r region. So that will be B into, and area will be, we say pi into small r square. Now take it out. So this will be E into 2 pi small r will be minus, and take this out. This will be pi small r square. And then I can say over here dB divided by dt. Now guys, this pi and this pi square and r will cancel. So electric field will be minus r by 2, and then we say dB divided by dt. This is the electric field. Okay. This is the electric field inside the region of magnetic field. Let's suppose if I ask you, induced electric field outside the region of varying magnetic field. Like I say magnetic field is, let's suppose, present in this region. Magnetic field is, let's suppose, present in this region at what r distance? And my dear friends, you have to tell me the electric field. You have to tell me the electric field in this region. You have to tell me the electric field in small r region. Right now, we say you have to tell me the electric field outside the region of the magnetic field. This is the region of magnetic field, and this is the ring. Or the loop, circular loop. Now, what is the formula I'm supposed to use? Closed line integral, we say EDL. Closed line integral EDL is equal to d phi minus d phi divided by dt. Okay. Now guys, if this is the ring, you have to take right now here small element dl, and here electric field will be E. So I can say, sir, take this electric field out. It will be closed line integral dl is equal to minus d by dt of magnetic field into area. So what is this closed line integral in this case? You say, sir, this will be, sir, if you take this small element over here, if you add all of these small elements, it will be simply, that is 2 pi small r equals to minus, we say, d by dt of magnetic field into area. Now, if you, here, you have to take that area through which the flux is changing. Guys, you have to take the area through which the flux is changing. Flux changes through this entire area, and this entire area is present in this whole region. Okay, if I say, sir, flux is changing from this side also, am I supposed to take this flux also? No. You have to take only which is that flux which is present in this small r region. like in the previous case, you took only that flux which is changing in the small r region. Here also, you have to take that flux only which is present in the small r region. So that is this much flux which is in the capital R region. Unfortunately, it is in the R region only, in a capital R region. So I can say that will be pi into R square. Here I have to take capital R. Previously, it was small r. So this pi and this pi. Okay. Then I can write in this particular case, electric field will be, so take this R out. So this will be minus R square divided by 2R dB divided by dt. So this will be the electric field in this case. Tell me, is this clear? Is this clear, or do you want me to repeat it? Guys, tell me in the chats. Is this clear? See, guys, what I'm trying to say is that here, this is the formula to find the electric field. If you take this electric field out, then integration of dl. What is this dl? dl is the small element of the ring. This will be the ring. This is the ring over here. Ring is present in the small r radius. Okay. So if you integrate this, you will get 2 pi r. And then this magnetic field into area. This area, you have to take area of that ring. Area of this small r ring, because in this only magnetic field is changing. So magnetic field is changing through, sir, magnetic field is changing in the capital R region. Yes. But you have to take only that much of field which is present in the small r, because this much only will create the electric field. Because this much only is present inside the ring, not away, what we are supposed to do with the outside magnetic field. So that's why here in this area you are putting pi small r square. But in this case, if you take this ring, inside the ring, how much is the magnetic field? All of this. So that's why in this case you are taking pi into capital R square. That's it. So with this we are done with the chapter. With this, we are done with the chapter. So thank you so much, guys. Okay. Thank you. Okay. So I would want you guys to comment down below when I end the live stream. Okay. I would want you guys to tell me how was the session, each and every single thing. So that's all for today, my dear friends. Take care and bye-bye. So make sure you comment by your heart. And if you are not like this session yet, I would want you guys to smash the like button as soon as possible. Okay. So thank you so much, guys. Take care. Do comment later on, okay?